Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, questions wander at an easy pace, and the universe is invited to settle in quietly beside you for a while. Tonight's gentle exploration drifts upward, not toward something small or distant, but toward a pattern of stars that most of us recognize without ever quite understanding how large it really is. We're going to spend some time with Sagittarius, the Archer, a familiar shape in the sky that feels like it belongs neatly between its neighbours, as if it were a tidy picture pinned onto the night. But size in space rarely behaves the way our eyes expect it to, and what looks like a simple constellation may stretch far beyond what imagination first allows. Before we begin easing into that thought, I have a small curiosity of my own. Where are you listening from tonight? Are you wrapped in blankets somewhere quiet, or letting this play softly as the day finally loosens its grip? And what time is it in your little corner of the world right now? It is always a strange and comforting idea to think about all of us scattered across different hours, different skies and different rooms, arriving at this same moment together. If you find this calm and meandering journey soothing, or even just pleasantly distracting from the busyness of the day, you are warmly invited to like the video or subscribe. It helps this quiet pocket of science reach others who might be looking for something gentle to fall asleep to. Now, let's begin easing our thoughts upward, away from the floor and the walls and the glow of screens, and toward the soft, distant light of stars that have been shining long before any of us thought to look up and ask how big they really are. When most people hear the word Sagittarius, they picture a shape. Maybe it is the Archer, drawn in lines between bright points of light, or perhaps the more casual version, the teapot shape that stargazers like to point out on warm summer nights. It feels contained, like a small picture framed by the darkness around it. You can point to it with a finger, trace it with your eyes and say, there it is. That sense of there, of something being located in a neat patch of sky, is one of the most comforting illusions astronomy gives us. But the sky is not a flat surface. It is not a dome with stars pinned into it like glitter on velvet. What you're really seeing when you look at Sagittarius is a set of stars scattered through three-dimensional space, some relatively nearby, others unimaginably far away, all lined up by chance from your particular viewpoint on Earth. The shape exists in your perspective, not in the universe itself. And once you start to think about that, the idea of measuring how big Sagittarius is becomes a lot more interesting. Let's begin with how we usually talk about size in the sky. Astronomers often use something called angular size. Instead of measuring how wide something is in kilometers or light years, they measure how much of your field of view it takes up. The moon, for example, covers about half a degree of the sky. If you hold your little finger up at arm's length, it roughly matches that width. Sagittarius as a pattern spans a much larger angle. From one end of its commonly recognized outline to the other, it stretches across a chunk of sky that would take several of those little fingers laid side by side to cover. So in terms of appearance, Sagittarius is already quite large. It occupies a generous section of the southern sky, especially for observers in the northern hemisphere during summer. But that is only the size of the picture, not the size of the thing. It is like judging the size of a mountain range by looking at a postcard. You see the outline, the silhouette, but you have no sense of how far it stretches behind the image. To get closer to the real scale, you have to think about the distances to the individual stars that make up Sagittarius. Some of them are a few hundred light years away, others are thousands of light years distant. A light year, just to pause and gently remind ourselves, is the distance light travels in 1 year. Since light moves at about 300,000 kilometers per second, 1 light year is nearly 9.5 trillion kilometers. And we are talking about stars that are not 1 or 2 of those units away, but hundreds and thousands of them. Take one of the brighter stars in Sagittarius, Caus Australis, for example. It sits roughly 140 light years from Earth. That already means the light reaching your eyes tonight left that star back when people on Earth were living without electricity, without cars, without the idea of space travel. Other stars in the same constellation are much farther. Some are more than 1,000 light-years away. That means the light you see now began its journey when human civilization was still in its earlier stages, when writing itself was a relatively new idea. So when you draw a line between those stars in your mind, you are connecting points that are not only separated across space but across time. The shape of Sagittarius is a kind of time collage, a mix of ancient light and slightly less ancient light, all arriving together in this moment. Now imagine trying to stretch a measuring tape between those stars, not across the sky, but through space. If you could travel from the nearest of Sagittarius's bright stars to one of the farthest, you would be crossing hundreds or even thousands of light years. That is not a trip you could make in a lifetime, or in 1,000 lifetimes, using any technology we currently understand. Even at the speed of our fastest spacecraft, it would take tens of thousands of years just to reach the nearest of them. So already, the size of Sagittarius in physical terms becomes something vast and hard to hold in the mind. It is not a cluster where stars are born together and remain relatively close, like the Pleiades. It is a loose, accidental alignment of stars scattered across a huge volume of the Milky Way. And that brings us to another layer of scale that makes Sagittarius especially interesting. When you look in the direction of this constellation, you are not just looking at a handful of stars, you are looking toward the centre of our galaxy. The Milky Way is a barred spiral galaxy, a vast disk of stars, gas and dust, about 100,000 light-years across. Our solar system sits in one of its spiral arms, far from the centre, about 26,000 light-years away, and Sagittarius points almost directly toward that crowded, energetic heart of the galaxy. So in that patch of sky, behind the familiar pattern of bright stars, there are billions upon billions of other stars, most of them too faint or too obscured by cosmic dust to see with the naked eye. There are glowing nebulae where new stars are being born. There are dense star clusters packed so tightly that their stars pass within a fraction of a light-year of each other. And there is something even more remarkable. At the very centre of the Milky Way, in the direction of Sagittarius, lies a supermassive black hole. It is called Sagittarius, a star, and it has a mass about 4 million times that of our Sun. It does not look like much from here. It is hidden behind clouds of dust and gas, and it does not glow brightly on its own. But its gravitational influence shapes the motion of stars in the galactic core, pulling them into fast, tight orbits that astronomers can track with incredible precision. So when you ask how big Sagittarius is, you're not just asking about a shape of stars, you're asking about a window that opens onto the deepest, densest and most dynamic region of our entire galaxy. Let's try to picture the volume of space involved. Imagine a box in space stretching from the nearest visible stars of Sagittarius out toward the galactic centre and beyond. That box would be tens of thousands of light-years deep. Inside it, there would be clouds of gas light-years wide, star clusters spanning dozens of light-years, and empty regions so vast that our entire solar system would be lost inside them without touching anything. Even the individual stars in Sagittarius are not small things. Many of the brightest ones are giants, stars that have swollen to many times the size of our Sun as they age. If you placed one of them where our Sun is, it might extend past the orbit of Mercury, or even Venus. So the constellation is not just large in terms of distance between points, but also in terms of the physical size of the objects that make it up. And yet, for all of this scale, Sagittarius still fits comfortably into a corner of the sky when you look up. That contrast between how it appears and what it actually represents is part of what makes astronomy such a quiet kind of wonder. You can stand in a backyard or on a balcony, glance up at a simple pattern of stars and unknowingly be staring down a corridor that leads to the core of a galaxy and a black hole millions of times more massive than the star that warms your face each morning. It is also worth thinking about how human culture has interacted with this patch of sky. Long before telescopes or knowledge of galaxies, people saw Sagittarius as a figure, a centaur with a bow, or sometimes just a bow itself. In other traditions, it became a teapot pouring a stream of the Milky Way into the sky. These interpretations were based entirely on the flat visual pattern. No one imagined the three-dimensional depth behind it, and yet, even without knowing, they were still pointing stories toward one of the most significant directions in the universe. If you could leave Earth and travel outward, rising above the plane of the Milky Way, and then look back, Sagittarius would not look like a shape at all. The stars that seem connected would scatter into a loose, uneven cloud. Some would be far in front, others far behind. The teapot would dissolve, and in its place you would see the true structure of the galaxy, a glowing disk with a bright, crowded centre. That thought alone begins to stretch the idea of size. Sagittarius is not a thing you can walk around or fly past in a neat path. It is a perspective, a direction, a slice of the galaxy that happens to line up in a way our eyes can recognize. Even the boundary of the constellation itself is a human decision. Modern astronomy has drawn official borders around each constellation, dividing the sky into 88 regions like a giant celestial map. Sagittarius's borders cover about 867 square degrees of sky, making it one of the larger constellations. That is a measurable, defined area. But in space there is no line where Sagittarius ends and the next constellation begins. The stars and clouds and clusters simply continue. So in a way, asking how big Sagittarius is becomes a question about how we choose to define things in a universe that does not come with labels or edges. We draw lines in the sky because it helps us navigate, remember, and share what we see. But the universe itself does not follow those lines. As you sit or lie there listening, you might imagine that section of the sky slowly rotating overhead as Earth turns. In a few hours, Sagittarius will move, not because it is travelling through space in that moment, but because you are. The planet beneath you is spinning, carrying your viewpoint along, changing the angle from which you see those distant stars. That movement is another quiet reminder of scale. Earth's rotation feels fast to us. Day and night pass in a steady rhythm. But compared to the slow drift of stars through the galaxy, it is a kind of quick dance on a very small stage. And yet, despite all this vastness, Sagittarius is also intimate in a way. Its light ends in your eyes. The photons that left those stars hundreds or thousands of years ago complete their journey on your retina, triggering tiny electrical signals in your brain that become an image, a recognition, a thought. The entire scale of the constellation, the galaxy, and the space beyond collapses into a moment of perception inside your head. That is one of the gentler paradoxes of astronomy. The biggest things we can imagine are known to us only through the smallest of interactions. Tiny particles of light meeting tiny cells in our eyes. Step outside on a warm evening, or imagine doing so if you're already tucked in somewhere comfortable, and let your eyes adjust to the dim glow of the sky. At first, you notice only the brightest points, the ones that seem to announce themselves without effort. Then, as your vision softens and settles, more stars quietly appear, like small notes being added to a long, slow melody. This is how most encounters with Sagittarius begin, not with a sudden realization of its presence, but with a gradual recognition that this part of the sky is more crowded, more textured, more alive with distant light than many others. During the summer months in the northern hemisphere, Sagittarius rises in the southern sky as the evening deepens. It never climbs very high for many observers, often lingering close to the horizon, partly veiled by the thicker layers of Earth's atmosphere. That low position can make it seem modest, even shy, compared to bold constellations that stride overhead. Yet, if you give it time and attention, you start to notice something different about this region. The darkness here is not empty. It is layered, almost cloudy, streaked with faint bands and patches that hint at something far larger than the individual stars you can pick out. What you're seeing, though you might not immediately recognise it as such, is the Milky Way itself. In the direction of Sagittarius, our line of sight runs straight into the dense central plane of our galaxy. The pale, glowing band that stretches across the sky is not a single object, but the combined light of countless stars, so many and so closely packed that their individual points blur together into a soft, luminous haze. This is one of the first clues that Sagittarius is not just a pattern of stars, but a doorway into a deeper, richer part of the universe. When you look here, you are not looking out into the quieter suburbs of the Milky Way, where our own solar system resides. You are looking toward the bustling downtown, where stars crowd together in greater numbers, where clouds of gas and dust pile up, and where the gravitational pull of the galactic centre shapes the motion of everything around it. On a clear, dark night, far from city lights, this region can be almost overwhelming. The sky does not feel like a simple backdrop anymore. It feels textured, layered, as though you could reach into it and brush your fingers through a glowing mist. The stars of Sagittarius sit in front of this luminous background, their brighter points standing out against the softer glow behind them, like lanterns hung in front of a distant city skyline. But even among these brighter points, there is a quiet variety. Some of the stars in Sagittarius shine with a steady white light. Others have a warmer golden tone. A few lean toward a faint subtle orange or red. These colours are not just decorative. They are clues to the star's temperatures, sizes and stages of life. Hotter stars burn blue-white. Cooler ones glow redder, and in between lie a whole spectrum of stellar personalities. One of the gentle joys of spending time with this part of the sky is noticing how your perception changes the longer you look. At first, Sagittarius might appear as a loose cluster of brighter points, perhaps forming that familiar teapot shape people like to mention. But as your eyes adjust, you start to see the fainter stars filling in the gaps. The shape becomes less of a simple outline, and more of a dense, scattered field. It begins to feel less like a drawing and more like a swarm, a drifting collection of lights at different depths and distances. This scattered quality is not an illusion. The stars of Sagittarius are not bound together in a tight group. They are not siblings born from the same cloud at the same time, travelling through space as a family. Instead, they are neighbours only in our line of sight. In reality, they occupy a wide range of positions within the Milky Way, separated by hundreds or thousands of light years. Imagine standing in a long, straight hallway lined with open doorways. Some doors are close to you, others far down the corridor. If you look straight ahead, all the door frames might appear stacked on top of each other, forming a single flat pattern. But if you were to walk through the hallway, you would discover the depth, the spacing, the long stretches between each one. Sagittarius is a bit like that hallway. The pattern you see in the sky is a projection, a flattening of a three-dimensional arrangement into a two-dimensional picture. Among the stars that make up this picture are some that are relatively close in cosmic terms. A few hundred light-years is still an enormous distance by everyday standards, but in the context of the galaxy, it is nearby. These stars are part of our local spiral arm, sharing the general motion of the Sun as it orbits the galactic centre. Others lie much farther away, deeper into the crowded regions of the Milky Way. Their light has travelled for thousands of years to reach you, passing through clouds of dust that dim and redden it along the way. This is why some parts of Sagittarius appear darker, not because there are fewer stars there, but because thick lanes of interstellar dust block their light from view. These dark streaks are like silhouettes of invisible clouds, outlined by the glow of stars behind them. If you could see in wavelengths beyond visible light such as infrared, much of that hidden structure would suddenly come into view. Telescopes designed to look in those ranges reveal a sky in Sagittarius that is packed with activity. There are star-forming regions where new suns are igniting inside dense clouds. There are massive clusters where stars are born in groups, lighting up their surroundings with radiation and stellar winds. There are remnants of exploded stars, expanding shells of gas left behind by ancient supernovae. All of this complexity sits behind the simple pattern you might casually point out to a friend on a summer night. It is a reminder that what we see with our eyes is only a thin slice of what is really there. The low position of Sagittarius in the sky for many observers adds another layer to the experience. When a constellation hugs the horizon, its light passes through more of Earth's atmosphere before reaching you. The air acts like a filter, scattering some of the light, blurring some of the detail, and sometimes tinting the stars with a faint shimmer of colour. This can make the region look softer, more diffuse, as though it is half remembered rather than sharply defined. There is something fitting about that softness, given how much of Sagittarius is hidden from direct view anyway. Even with powerful telescopes, much of the galactic centre remains obscured by dust. Astronomers piece together its structure using radio waves, infrared light, and careful measurements of how stars move under the influence of gravity. The clear, bright picture we might wish for simply does not exist in visible light. Instead, there is a layered, veiled complexity that has to be explored indirectly. If you let your mind wander a little, you can imagine what it would be like to travel in that direction. The familiar stars would slowly drift apart as you move through space. Some would grow brighter and larger as you approached them, then slide past and fade behind you. Others would remain distant, barely changing, until, over very long times, they too began to shift. The background glow of the Milky Way would gradually resolve into individual points, each one a sun with its own planets, its own history, its own future. In that sense, the scattered stars of Sagittarius are like signposts along a much longer road, pointing toward the deeper interior of the galaxy. They mark a direction rather than a destination. There is no single place you arrive at when you reach Sagittarius. There is only more space, more stars, more structure unfolding as you go. This perspective can gently change how you think about the night sky. Instead of a flat map overhead, it becomes a vast landscape, with hills and valleys of star density, with near and far, with foreground and background. Some constellations feel like they sit on the surface of that landscape, their stars relatively close together in space. Sagittarius, by contrast, feels like a window into depth, into layers stacked behind layers. Even the way the Milky Way looks here reflects that depth. In darker skies, you can see bright star clouds, regions where the galaxy seems to thicken and glow. You can also see dark rifts, places where something is missing. But those missing places are not empty. They are full of dust, cold and dense, waiting for gravity to slowly gather it into new stars. The scattered appearance of Sagittarius is, in part, a map of where that dust lies, carving shapes out of the background light. As you continue to spend time with this region, you might notice that it does not stay the same from night to night, or even from hour to hour. Not because the stars themselves are moving in any noticeable way, but because your angle of view is changing as Earth turns. The Milky Way tilts, the teapot shape rotates, and different parts of the star field rise or sink into the haze of the horizon. There is a quiet, steady rhythm to this motion, one that has been playing out for as long as humans have been looking up. Long before there were names like Sagittarius, people watched this same region of sky rise and fall with the seasons. They noticed that when it appeared in the evening, it often coincided with the warmth of summer in the northern hemisphere. The sky and the calendar became linked in subtle ways, the stars serving as markers of time as much as of space. In some cultures, the dense star fields here were seen as a river, a road, or a path for spirits. In others, the darker patches were as meaningful as the bright ones, seen as animals or shapes carved out of the glowing background. These interpretations were all responses to the same scattered, layered appearance, the same sense that this part of the sky was more than just a few points of light. Modern astronomy, with all its instruments and measurements, has added detail to that sense rather than replacing it. We now know about star clusters hidden in the dust, about clouds collapsing under gravity, about a black hole quietly anchoring the galaxy at the centre of it all. But when you stand under the sky and look towards Sagittarius, you're still experiencing it the way people always have, as a patch of light and shadow that invites curiosity rather than providing clear answers. That invitation is part of what makes this constellation such a gentle place to linger, especially in a quiet moment like this. You do not need to identify every star or remember every distance. You can simply let the scattered light suggest depth, distance, and scale without pinning them down to numbers. At some point, usually without realizing it, most of us grow up thinking of constellations as things. Not just patterns, but actual objects in space, like clusters or groups that belong together. We learn their names, or we see their outlines drawn in books or apps, and it becomes natural to imagine them as if they were floating shapes, neatly arranged and somehow connected out there in the darkness. Sagittarius, the Archer, feels like one of these things, a recognizable presence in the sky that you can point to and say, that is it. But the deeper you look, the more that simple idea begins to soften and stretch, until you realize that a constellation is not really an object at all. It is something closer to an agreement, a shared way of seeing, a map drawn on a surface that does not truly exist. To understand this, it helps to think about how we normally interact with physical objects. If you walk around a chair, it stays the same. You can view it from different angles, but it remains a single, solid thing occupying a specific place in space. A mountain does not change its shape just because you move a few steps to the left or right. But a constellation does. If you could move far enough through space, even a relatively short cosmic distance, the familiar shape would begin to unravel. The reason is simple and strange at the same time. The stars that form a constellation are not tied together in any meaningful physical way. They are not bound by gravity as a group. They did not form from the same cloud at the same time. They are not travelling together through the galaxy. They just happen to line up from our particular viewpoint on Earth in a way that our brains recognise as a pattern. Imagine standing in a field and looking toward a distant row of trees. One tree might be close to you, another far away, and another somewhere in between. From where you stand, their trunks and branches might overlap in your field of view, forming what looks like a single line. But if you were to walk toward them, that line would break apart. The nearer tree would grow larger quickly, while the distant one would barely seem to change. The alignment would dissolve. That is what would happen to Sagittarius, or any constellation, if you could move through space instead of just across the surface of Earth. This idea can feel a little unsettling at first, because it challenges the sense that the sky is a stable, structured place. We like to think of it as a kind of ceiling, with fixed pictures painted on it. But in reality, the sky is more like a window into a vast three-dimensional environment, and the pictures only exist because we are looking through that window from one very specific spot. If you were to travel a few dozen light-years away from Earth, not even very far by galactic standards, the shapes of familiar constellations would already look different. The stars would still be there, but their positions relative to one another would shift. Lines would bend, angles would change. Some stars that appear close together now would drift apart, while others that seem far apart might line up more neatly. This is not just a thought experiment. Astronomers can model how constellations will look in the future, based on the known motions of stars. Over tens of thousands of years, the patterns we recognize today will become unrecognizable. The Big Dipper, Orion, Sagittarius, all of them will slowly transform into new arrangements, new accidental alignments that future skywatchers might name and draw in their own ways. So if a constellation is not an object, what is it? One way to think about it is as a kind of projection. We are taking a three-dimensional distribution of stars and flattening it onto a two-dimensional surface in our minds. The result is a picture that feels real. even though it is an artifact of perspective. This is something our brains are very good at doing. We look for patterns automatically. We connect dots. We find shapes in clouds, faces in shadows, animals in the arrangement of stars. It is part of how we make sense of a complex world. The night sky, with its thousands of points of light, is a perfect canvas for this tendency. In the case of Sagittarius, the pattern has been seen and named in many different ways across cultures and time. In Western astronomy, it became an archer, often depicted as a centaur drawing a bow. In some traditions, it was seen more simply as a bow itself. In others, especially in modern stargazing, it became a teapot. None of these interpretations are more correct than the others. They are all ways of organising the same scattered stars into something meaningful. This cultural layer adds another dimension to the idea that a constellation is not an object. It is not just a physical illusion, but also a social one. The shape exists because people agree that it exists, because it has been named, taught, drawn, and passed down. Even the official boundaries of constellations, as defined by modern astronomy, reflect this. In the early 20th century, astronomers decided to divide the entire sky into 88 regions, each assigned to a constellation. These regions have precise borders, measured in right ascension and declination, like latitude and longitude on Earth. Sagittarius in this system is not just a shape, but a defined area of sky. But those borders do not correspond to anything in space. There is no line out there where Sagittarius ends and Capricornus or Scorpius begins. Stars and gas and dust flow across those imaginary boundaries without any regard for the names we've given them. This can be a gentle reminder of how much of our understanding of the universe is shaped by the tools and concepts we use to describe it. Constellations are useful. They help us navigate the sky. They give us reference points. They make it easier to talk about where things are, but they are not fundamental features of the cosmos. They are overlays, like grid lines on a map. If you look at a globe of Earth, the lines of longitude and latitude are incredibly helpful for finding places. But they are not real in the physical sense. You cannot walk along the equator and trip over it. You cannot dig up a meridian. They exist because we agreed to draw them. Constellations are similar. They are part of our mental coordinate system for the sky. This becomes especially clear when you think about how the sky would look from another planet, or even another star system. From Mars, the constellations would already be slightly different. From a star 100 light-years away, they would be completely transformed. Sagittarius might not exist as a recognizable pattern at all, and yet the stars themselves would still be there. The galactic center would still be in roughly the same direction. The deep structure of the Milky Way would remain. What would change is the picture drawn on top of it. This distinction between what is physically there and what we perceive is one of the quieter, more subtle lessons of astronomy. It invites a kind of humility. We realize that many of the things we take for granted as real are, in some sense, interpretations. That does not make them meaningless. On the contrary, it gives them a different kind of value. The fact that people across thousands of years and cultures have looked at the same scattered stars and found stories in them is part of what makes constellations special. They are not just markers in space. They are records of human imagination. In Sagittarius, those stories often connect to themes of hunting, aiming, direction and movement. An archer draws a bow and sends an arrow forward. There is a sense of purpose, of pointing, of focus. It is interesting, in a quiet way, that this figure is associated with the direction of the galactic center, a place of immense gravitational pull and energy, where stars move in fast, tight orbits around something they cannot see. That connection was not intentional, of course. Ancient sky watchers did not know about black holes or galactic cores. But the coincidence adds another layer to the experience of looking at this part of the sky. The story we tell ourselves happens to align, loosely, with a region of space that is genuinely dynamic and powerful. Still, it is important to keep the distinction clear. The archer is not really there. The teapot is not really pouring anything. These are ways of seeing, not things being seen. This can become even more apparent when you use a telescope or a pair of binoculars. When you zoom in on Sagittarius, the familiar shape disappears. Instead of a simple pattern, you find yourself surrounded by stars. The field of view fills with points of light, some bright, some faint, some clustered, some scattered. The sense of a single, coherent figure dissolves into a complex layered scene. You might find a star cluster, a tight knot of dozens or hundreds of stars bound together by gravity. That is an object. You might find a nebula, a cloud of gas and dust glowing under the influence of nearby stars. That is an object. But the constellation itself vanishes under scrutiny, like a picture that falls apart when you look too closely. There is something quietly comforting about that. It suggests that the universe does not come pre-packaged into neat categories. The divisions we use are tools, not truths. They help us explore, but they are not the final word on what exists. This idea can ripple outward into other areas of thought. Just as constellations are not really objects, many of the things we name and define in our daily lives are, in some sense, groupings and boundaries we create for convenience. Countries, time zones, even the concept of a day or a year are based on natural phenomena, but they are shaped and formalized by human choice. In the sky, the natural phenomena are the stars, the gas, the dust, the gravitational forces, the slow motion of everything through the galaxy. The constellations are our way of organizing that into something we can remember and share. When you look at Sagittarius with this in mind, it can feel less like you're seeing a thing and more like you're participating in a tradition. You're joining a long line of people who have looked at the same scattered lights and drawn lines between them, both literally and figuratively. This does not diminish the wonder. If anything, it adds a layer of quiet connection. The shape you see is not just a product of the universe. It is also a product of human perception, creativity, and curiosity. At the same time, understanding that Sagittarius is not an object can make its true scale feel even larger. If there is no physical boundary, no edge where it stops, then the region it points toward, the dense heart of the Milky Way, becomes the real focus. The constellation becomes more like an arrow or a signpost, directing your attention rather than containing it. In that sense, Sagittarius is less a place and more a direction. It tells you where to look if you want to peer deeper into the structure of our galaxy. It marks a pathway through space, not with a solid line, but with a loose arrangement of stars that happen to guide your gaze. As you sit with that idea, you might notice how your sense of the sky shifts. Instead of a collection of pictures, it becomes a field of directions, depths, and layers. Each constellation is a doorway rather than a destination, and that way of seeing sets the stage for thinking about measurement in a different way. If Sagittarius is not a thing you can put a boundary around, then what does it mean to say how big it is? Are you measuring the angle it covers in the sky, the distances between its nearest and farthest stars, or the vast swath of the galaxy it points toward? Those questions begin to open up a broader perspective, one where size is not a single number, but a set of relationships. Relationships between you and the stars, between one star and another, between our small corner of the Milky Way and its distant, crowded centre. It is enough to let the idea settle that Sagittarius, like all constellations, is a pattern we carry with us rather than a structure that exists on its own. A way of seeing, not a thing being seen. When you begin to think of a constellation as a picture rather than an object, the next natural question is how anyone could possibly measure something that does not really exist as a single thing. If Sagittarius is a set of stars scattered through space, lined up by chance from our viewpoint, then measuring its size becomes an exercise in measuring distances that do not lie neatly along one line. It becomes a matter of turning light, motion, and tiny shifts in position into a kind of cosmic ruler. This is where astronomy quietly transforms from skywatching into something closer to detective work. There is no tape measure long enough to stretch from Earth to a star. There is no way to send a probe fast enough to touch even the nearest ones within a human lifetime. Everything we know about how far away the stars are comes from studying the light they send us and how they appear to move against the background of the sky. One of the gentlest and most intuitive methods astronomers use is called parallax. The idea is simple, even if the distances involved are not. If you hold your thumb up in front of your face and look at it with one eye closed, then switch to the other eye, your thumb appears to jump slightly against the background. That apparent shift happens because your two eyes are looking from slightly different positions. Now imagine doing the same thing, but instead of moving your eyes, you let Earth move. As our planet orbits the Sun, our viewpoint changes by a distance of about 300 million kilometers from one side of the orbit to the other. For nearby stars, this change in position causes a tiny apparent shift against the much more distant background stars. That shift is incredibly small, often less than the width of a human hair held at arm's length, but with careful instruments, it can be measured. From that tiny angle, astronomers can use geometry to calculate how far away the star must be. The smaller the shift, the farther away the star is. This method works well for stars within a few thousand light years of Earth, which covers some of the nearer members of Sagittarius. But Sagittarius, as a region of the sky, points far beyond that. Many of the stars and structures associated with it lie tens of thousands of light years away, near the galactic centre. For those distances, parallax becomes too subtle to measure directly, even with the most precise space-based observatories. So astronomers turn to other methods, ones that rely on understanding how stars behave rather than how they shift in position. One of these approaches uses something called standard candles. The name sounds simple, but the idea behind it is powerful. If you know how bright something truly is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. A candle held close to your face looks bright. The same candle across a large room looks dim. The difference tells you something about the distance. In space, certain types of stars behave in very predictable ways. One example is a class of stars called Cepheid variables. These stars rhythmically brighten and dim over time, pulsing like slow, steady beacons. The key detail is that the period of their pulsation is directly related to their true brightness. By measuring how long it takes for a Cepheid to complete one cycle of brightening and dimming, astronomers can determine how luminous it really is. Then, by comparing that to how bright it looks from Earth, they can estimate its distance. Cepheid variables have been found in and beyond Sagittarius, especially in the direction of the galactic centre. They act like mile markers along a road that disappears into the depths of the Milky Way. There are also other kinds of standard candles, such as certain types of exploding stars called supernovae. While these are not common in our galaxy, when they do occur, they can briefly outshine entire star systems. Their peak brightness is well understood, which allows astronomers to measure distances to faraway galaxies. While this method reaches far beyond Sagittarius, it helps place our own galaxy and the direction of its centre into a larger cosmic context. But measuring distance alone does not fully answer the question of size. Sagittarius is not a straight line of stars stretching away from us. It is a wide, layered region filled with objects at many different depths. To understand its scale, astronomers also look at how stars move. Every star in the Milky Way is orbiting the galactic centre, including our Sun. These motions are not random. They follow paths shaped by the combined gravity of billions of stars, clouds of gas, and the massive black hole at the core. By measuring how fast stars in different parts of the galaxy are moving, astronomers can map out the structure and mass of the Milky Way. In the direction of Sagittarius, these measurements become especially interesting. Stars near the galactic centre move at tremendous speeds, sometimes hundreds of kilometers per second, as they circle the deep gravitational well at the heart of the galaxy. By tracking these motions, scientists can estimate how far away the centre is and how large the central region must be. Some of the most detailed measurements come from watching individual stars near Sagittarius A star, the supermassive black hole at the galactic center. Over years and decades, astronomers have observed these stars tracing out full or partial orbits. From those paths, they can calculate both the mass of the black hole and the distance to it. That distance, about 26,000 light-years, becomes a kind of anchor point for measuring everything else in that direction. So when you think about the size of Sagittarius, part of what you're really thinking about is a corridor that stretches from our solar system out to that central region and beyond. That corridor is tens of thousands of light-years long, but it is also wide, spanning a thick slice of the galactic disk. Another tool astronomers use is the study of interstellar dust and gas. These clouds do not just block light, they also emit and absorb specific wavelengths that can be detected with radio and infrared telescopes. By mapping where these clouds are and how their properties change with distance, scientists can build a three-dimensional picture of the galaxy's structure in the direction of Sagittarius. Radio observations, in particular, are useful because radio waves can pass through dust that blocks visible light. This allows astronomers to see deep into the galactic plane, revealing star-forming regions, molecular clouds, and the spiral structure of the Milky Way. Sagittarius happens to sit near the line of sight, where one of the galaxy's spiral arms curves toward the center, adding another layer of depth and complexity. All of this data, from parallax standard candles, stellar motions, and radio mapping, comes together in large, detailed models of the galaxy. These models are not static. They are constantly refined as new measurements come in. Space missions like Gaia, which is mapping the positions and motions of more than 1 billion stars, are transforming our understanding of how the Milky Way is shaped. Gaia's measurements are especially relevant to Sagittarius because they reveal how stars in that region are moving in 3 dimensions. This allows astronomers to distinguish between stars that only appear close together in the sky and those that are actually near each other in space. It helps separate the foreground from the background, the nearby from the distant, and the chance alignments from genuine groups. Through this work, Sagittarius becomes less like a flat picture and more like a layered sculpture, with stars and clouds arranged in a complex 3-dimensional structure. But even with all these tools, there is a limit to how precise our measurements can be. Light can be dimmed or reddened by dust. Stars can vary in brightness for reasons that complicate their use as standard candles. Motions can be influenced by unseen mass, such as dark matter, which does not emit light but exerts gravity. This means that our picture of Sagittarius, and of the galaxy as a whole, is always a work in progress. It is a best estimate, a carefully constructed model based on the information we can gather, rather than a perfectly mapped territory. There is something quietly fitting about that. The sky we see is itself a partial view, filtered by our atmosphere, limited by our senses. The measurements we make are an extension of that partiality, reaching further, but never quite reaching all the way. If you imagine trying to measure a foggy landscape at night with a flashlight, you might get a sense of what this process is like. You can see nearby objects clearly. Farther ones appear as vague shapes. Beyond that, there is only darkness. You can infer what might be there based on how the light fades, how shadows fall, how the ground feels underfoot. But you never get a complete, clear picture all at once. In the same way, Sagittarius is measured through a combination of direct observation and careful inference. Each method adds a layer of understanding, and together they build a sense of scale that is far richer than a single number could convey. Another aspect of measurement that often goes unnoticed is time. Because light takes time to travel, looking at distant parts of Sagittarius means looking into the past. A star 1,000 light-years away is seen as it was 1,000 years ago. The galactic center, 26,000 light-years away, is seen as it was when early human civilizations were just beginning to take shape. So the picture you see in the sky is not just drawn by distance but by time as well. Different parts of Sagittarius are frozen at different moments in their histories, all presented to you at once. The region is not just wide and deep, it is also layered in time. This adds another subtle dimension to the idea of size. When you measure Sagittarius, you're not just measuring how far it stretches through space, but how far it stretches through history. The light from its farthest reaches has been travelling longer than recorded human history. The closer stars, by comparison, are sending you news from a much more recent past. If you let that thought settle, it can change how the sky feels. It becomes less like a snapshot and more like a collage, assembled from moments spread across thousands of years. Even the act of defining where Sagittarius begins and ends becomes more fluid in this context. Do you include only the stars that form the traditional pattern? Do you include the dense star fields and nebulae behind them? Do you include the galactic centre itself, which lies in that same direction but far beyond the bright foreground stars? Different astronomers might answer differently depending on what they're studying. A catalogue of bright stars will define Sagittarius one way. A survey of star-forming regions will define it another way. A map of the galaxy's mass distribution might use it simply as a direction, not a region at all. This flexibility reflects the deeper truth that Sagittarius is a label we apply to a complex layered portion of the universe. Measuring it is not about finding a single, definitive size, but about understanding the range of distances, structures, and depths that lie along that line of sight. The picture of Sagittarius is drawn by distance, time, and perspective, and that measuring it is a careful, patient process of turning tiny shifts in light into a map of something far larger than any of us can directly experience. If you were able to step away from the planet for a moment and look back at Earth as a small pale sphere floating in the dark, you would quickly notice something about the way it sits in space. It is not just drifting randomly. It is spinning, steadily, once every 24 hours, and it is also circling the sun, carrying every observer along a slow, graceful path through the Milky Way. That motion, quiet and constant, shapes everything you see in the sky, including how Sagittarius appears and disappears from view. From Earth, Sagittarius is not a fixed picture pinned to a permanent spot overhead. It is a seasonal visitor, rising and setting like the sun and moon, its presence tied to the time of year and the latitude from which you are watching. This alone is a gentle reminder that what we call the sky is not something outside of us, but something we are moving within. For observers in the Northern Hemisphere, Sagittarius is a constellation of summer evenings. As the days grow longer and warmer and the sun sets later, the Archer begins to climb into the southern sky after dusk. By midsummer, it reaches its highest point around midnight, lingering low but prominent, especially for those who can find a place away from city lights. In the southern hemisphere, Sagittarius enjoys a more commanding role. It climbs higher into the sky, often passing near the zenith, the point directly overhead. There, it is not a shy visitor near the horizon, but a central figure, surrounded by the glowing band of the Milky Way stretching across the darkness. The difference between these two views is striking, and it shows how much of our experience of the cosmos depends on where we stand on our rotating world. Latitude shapes the sky like a lens. From near the equator, Sagittarius can be seen high and clear, with much of the galactic centre region fully on display. From farther north, some of its southernmost stars barely rise above the horizon, and parts of the dense Milky Way backdrop remain hidden in the haze of thicker atmosphere. From far enough south, Sagittarius becomes a familiar, almost overhead presence, woven into the everyday pattern of the night. This variation adds another layer to the idea of size. The same region of space can feel small or expansive depending on how much of it you can see at once. A constellation that seems compact and modest from one place can feel broad and immersive from another. Even the time of night matters. When Sagittarius first rises, It emerges through the glow of the horizon, its stars softened by atmospheric scattering. The brighter ones appear first, while the fainter ones wait until the sky darkens fully. As the night deepens, more of the surrounding Milky Way becomes visible, and the constellation feels as though it is growing, not in reality, but in richness and detail. There is also the slow, nearly imperceptible motion of the stars themselves to consider. Over the course of a single night, Sagittarius moves from east to west across the sky, driven by Earth's rotation. But over much longer timescales, something else is happening. Earth's axis wobbles slightly like a spinning top in a motion called precession. This wobble takes about 26,000 years to complete a full cycle, and it gradually shifts the positions of the constellations relative to the seasons. Thousands of years ago, Sagittarius rose at different times of year than it does now. Thousands of years from now, it will rise at different times again. This means that the way Sagittarius fits into the rhythm of the year is not fixed. It drifts slowly across the calendar, reminding us that even our seasonal connection to the sky is temporary on a long enough timeline. From Earth, Sagittarius also carries a kind of visual signature that sets it apart from many other constellations. Because it sits in the direction of the galactic centre, it is surrounded by some of the richest star fields visible to the naked eye. This makes the region feel textured, layered, and almost three-dimensional, even though we are seeing it projected onto the dome of the sky. On a clear, dark night, you might notice bright patches in the Milky Way near Sagittarius, areas where the galaxy seems to thicken and glow. These are star clouds, regions where countless distant stars blend into a soft, luminous mass. Right beside them, you might see dark lanes, irregular shapes where the glow is missing. These are not empty spaces, but dense clouds of dust blocking the light from behind. This interplay of light and shadow gives Sagittarius a depth that can be felt even without knowing the details behind it. It is a place where the sky does not feel uniform. It feels like it has hills and valleys, bright ridges and dark hollows. From Earth, the most commonly recognized pattern in Sagittarius is the so-called teapot. It is a practical, modern way of identifying the brighter stars that form a rough, boxy shape with a spout and a handle. Once you see it, it is hard to unsee. The spout appears to pour a stream of the Milky Way into the sky, a playful image that captures something real about the dense star fields in that direction. This teapot shape is not ancient. It is a product of recent stargazing culture, a convenient way to help people find their way around the region. But it highlights something important about how we see from Earth. We latch onto a few bright points and use them as anchors, building a mental map that helps us navigate a much more complex background. Those anchor stars are the ones that define Sagittarius in most people's minds. They are relatively nearby, at least compared to the galactic centre, and they shine brightly enough to stand out against the haze of distant starlight. Without them, the region might feel too crowded, too diffuse to form a clear shape. So the Sagittarius we see from Earth is, in a sense, a foreground layer laid over a vast background. The bright stars are like signposts, while behind them lies the real bulk of the galaxy. This layered view can become especially clear when you use binoculars or a small telescope. The moment you magnify the region, the sky fills with stars. The neat outline of the teapot dissolves into a field of points. You might notice tight clusters where dozens of stars are packed into a small area. You might see faint cloudy patches that reveal themselves as nebulae, glowing gas clouds lit by nearby stars. One famous example is the Lagoon Nebula, a star-forming region in Sagittarius that can be seen even with modest optical equipment. To the naked eye, it appears as a faint smudge, barely distinct from the surrounding glow. Through a telescope, it becomes a complex structure of bright knots, dark lanes, and luminous gas, a place where new stars are actively forming. Seeing something like that can shift your sense of what the constellation is. It stops being just a pattern and starts to feel like a window into an active, evolving part of the galaxy. From Earth, our view of Sagittarius is also shaped by the atmosphere itself. The air above us is not perfectly transparent. It scatters light, absorbs certain wavelengths, and blurs fine detail. This is why stars near the horizon often twinkle more, their light passing through thicker layers of air that shift and distort it. Because Sagittarius often sits low in the sky for many observers, its stars can appear to flicker and shimmer more than those overhead. Colours can become more pronounced or more muted depending on the conditions. This gives the region a dynamic, almost restless quality, as though it is never quite holding still. Light pollution adds another filter. In cities and suburbs, the glow of streetlights and buildings can wash out much of the Milky Way, leaving only the brightest stars of Sagittarius visible. The constellation becomes a sparse outline rather than a rich textured field. This contrast between urban and dark sky views can be dramatic. In a truly dark location, Sagittarius can feel overwhelming in its complexity, a dense glowing mass of stars and shadows. In a bright city, it can feel modest, even unremarkable, a handful of points in a hazy sky. Both views are real, in the sense that they reflect what reaches your eyes from where you are. But they tell very different stories about what lies beyond. Another subtle factor in how Sagittarius appears from Earth is the tilt of our planet's axis. Earth is tilted about 23.5 degrees relative to its orbit around the Sun. This tilt is what gives us seasons, and it also determines how high or low different parts of the sky appear throughout the year. Because Sagittarius lies along the ecliptic, the path the Sun appears to follow across the sky, it is also part of the zodiac. This means that at certain times of year, the Sun passes through that region of the sky during the day, making Sagittarius invisible at night. During those months, it is there, but hidden in the daylight, its stars washed out by the brightness of the Sun. When Sagittarius finally emerges into the night sky again, it can feel like a return, a familiar presence reappearing after a long absence. That cycle, repeated year after year, weaves the constellation into the rhythm of time on Earth. From our perspective then, Sagittarius is not just a direction in space, it is also a marker in time. Its rising and setting help define seasons. Its presence or absence in the night sky becomes part of the annual pattern of the year. This connection between sky and calendar is ancient. Long before modern astronomy, people used the appearance of certain stars and constellations to mark planting seasons, migrations, and rituals. Sagittarius, rising in the warm months, would have been part of that web of seasonal knowledge. So when you look at it now, you're not just seeing stars, you're also seeing a thread of human history, a pattern that has been noticed and used for thousands of years. From Earth, Sagittarius also serves as a kind of reference point for finding other things in the sky. Once you identify its bright stars, you can use them to locate nearby constellations like Scorpius and Capricornus, or to trace the path of the Milky Way as it arcs across the heavens. In this way, Sagittarius becomes part of a larger map, a node in a network of visual landmarks that help us orient ourselves in the vastness above. But even as it helps us find our way, it quietly reminds us of how small our viewpoint is. Everything we see in Sagittarius is filtered through our position on a small, rotating planet, orbiting an average star, located in one of the outer arms of a large spiral galaxy. We're not looking at the galaxy from the outside like a photograph in a book. We are inside it, peering through its layers, trying to make sense of its structure from within. Sagittarius is one of the few directions where that structure reveals itself more clearly, where the density of stars and the depth of the field hint at the true scale of what we are part of. If you let your imagination drift for a moment, you can picture the Milky Way as a vast disk of light, with our sun embedded in one of its arms. Sagittarius points inward toward the crowded, luminous centre. When you look there, you are looking across a large fraction of the galaxy's diameter. That alone gives the region a sense of size that goes beyond the pattern of stars you can trace with your eyes. It becomes a line of sight that spans tens of thousands of light years, crossing spiral arms, star-forming regions, and clouds of dust, all the way to the heart of the Milky Way. From Earth, of course, you cannot see all of that directly. Much of it is hidden behind dust or too faint to register on your eyes, but knowing that it is there can change how the sky feels. The darkness behind the stars is no longer empty, it is full, layered, and active, even if you cannot see it. This awareness can add a quiet depth to the simple act of stargazing. A handful of points of light becomes a kind of cross-section through a galaxy. The archer rises and sets with the seasons, shaped by latitude, filtered by atmosphere, framed by the glow or darkness of the night around you. It is both a familiar pattern and a distant direction, a local landmark and a gateway to something far larger. When you begin to think about distance in space, especially the kind of distance that stretches beyond anything you have experienced on Earth, it can help to start close, or at least as close as the stars ever get. The nearest stars in the direction of Sagittarius are not neighbours in the everyday sense of the word, but they are the ones whose light reaches us with the least delay, whose presence in our sky is shaped more by their actual position in space than by the deep, layered structure of the galaxy behind them. Even so, near in astronomy is a word that carries a very different weight. Let's begin with a simple anchor. The closest star to our solar system is Proxima Centauri, a small, faint red dwarf about 4.24 light-years away. That distance alone is enough to remind us how isolated our Sun really is. If you could travel at the speed of the fastest spacecraft ever built, it would still take tens of thousands of years to get there. And yet, in cosmic terms, Proxima Centauri is practically next door. Now, when you turn your attention towards Sagittarius, you're not looking directly at Proxima Centauri or any of our immediate stellar neighbours. The constellation lies in a very different direction in the sky. The nearest stars that appear within its boundaries, the ones that make up the familiar pattern people point out on summer nights, are significantly farther away. Some of the brighter stars in Sagittarius are a few hundred light-years from Earth. That might not sound dramatic compared to the thousands of light-years that stretch toward the galactic centre, but it is still an immense span of space. Imagine light leaving one of these stars. It begins its journey through the darkness, travelling at nearly 300,000 kilometres per second. In 1 second, it could circle Earth more than 7 times. In 1 minute, it could travel from Earth to the Moon and back many times over. In 1 year, it covers nearly 9.5 trillion kilometres. Now imagine that process repeating year after year for 200, 300 or 500 years. Only then does the light finally reach your eyes. That means the nearest stars of Sagittarius are not being seen as they are now. You are seeing them as they were centuries ago. If something dramatic happened to one of them tonight, a sudden flare, or even a catastrophic explosion, it would not register on Earth for generations. One of the more prominent stars in Sagittarius is Caus Australis, also known as Epsilon Sagittarii. It sits roughly 140 light-years away. In the grand scale of the galaxy, that is still considered relatively nearby. But to put it into perspective, 140 light-years is about 1.3 quadrillion kilometres. That number is so large it almost stops being meaningful in everyday terms. If you tried to drive that distance at highway speed, say 100 kilometers per hour, without stopping, it would take you well over 1 billion years to arrive. You would outlast civilizations, continents, and perhaps even entire species, and still be on the road. Another bright star in the pattern, Nunki, is much farther. Its distance is estimated at around 230 light-years. Others push beyond that, reaching distances of several hundred light-years. These stars are part of the general stellar population of our spiral arm, the same broad region of the Milky Way where our Sun resides. This means that, in a sense, the nearest stars of Sagittarius are not exotic or unusual members of some distant part of the galaxy. They are neighbours in the same large neighbourhood, orbiting the galactic centre at roughly the same distance as we are, sharing the same general motion around the core. But even within this local context, their spacing is vast. Stars in our part of the Milky Way are typically separated by several light years. The region around our Sun is not crowded. It is more like a quiet countryside than a dense city. You could place our entire solar system inside the space between stars and still have room to spare. So when you look at the nearest stars of Sagittarius, you're looking at individual suns scattered through a wide, mostly empty volume of space. The pattern they form in the sky hides that emptiness. It makes them feel closer together than they really are. Another way astronomers determine how far these stars are is by measuring their parallax, the tiny shift in their position as Earth moves around the Sun. For stars a few hundred light years away, this shift is extremely small, but it is measurable with modern instruments. Space missions like Gaia have refined these measurements to an extraordinary degree of precision. Gaia is mapping the positions and distances of more than 1 billion stars in our galaxy, including many in Sagittarius. It can detect shifts in position that are smaller than the width of a human hair, seen from thousands of kilometers away. From these measurements, astronomers can build a 3-dimensional map of our local region of the Milky Way. They can see which stars in Sagittarius are truly nearby, and which ones only appear close because they line up along the same line of sight. This process often reveals surprising relationships. 2 stars that look almost side by side in the sky might be separated by hundreds of light years in space. One might be a foreground star, relatively close to Earth, while the other lies deep in the background, far closer to the galactic centre. So when we talk about the nearest stars of Sagittarius, we're really talking about the front layer of a much deeper structure. They are the first signposts along a long road that stretches inward across the galaxy. It is also interesting to consider the types of stars that appear in this nearer group. Many of the bright ones are giant or supergiant stars. These are stars that have reached a later stage in their life cycles, expanding to many times the size of our Sun. They shine brightly not just because they are close, but because they are physically large and luminous. This means that the pattern of Sagittarius is shaped in part by a selection effect. We see the stars that are both relatively nearby and relatively bright. There are countless smaller, dimmer stars in the same region of space that we cannot see with the naked eye at all. If you could somehow turn off the brightness limit of your vision, the sky in Sagittarius would fill with a thick, shimmering fog of faint points. The nearest stars would still be the nearest, but they would be just a small fraction of the total population in that direction. Thinking about the nearest stars also invites you to think about motion. Every star in the Milky Way is moving. They are not fixed points on a cosmic sphere. They orbit the galactic centre, and they also have their own individual motions relative to that general flow. The nearest stars in Sagittarius have what astronomers call proper motion, a slow drift across the sky over time. This drift is usually too subtle to notice in a single lifetime without precise instruments, but over thousands or millions of years, it becomes significant. If you could speed up time and watch the sky and fast forward, you would see the nearest stars gradually slide out of their familiar positions. The shape of Sagittarius would stretch and distort. Stars would move into and out of alignment. The pattern would change. This highlights another aspect of distance. The closer a star is to you, the faster it appears to move across the sky, because its actual motion translates into a larger apparent shift from your perspective. More distant stars move more slowly in apparent terms, even if their true speeds through space are similar. So the nearest stars of Sagittarius are not just closer in distance, they're also more dynamic in how they appear from Earth over long periods of time. They are the ones that will most strongly reshape the constellation's pattern in the far future. Another layer to consider is the environment these stars live in. Being part of the same general spiral arm as the Sun means they are embedded in similar conditions. They formed from clouds of gas and dust that were part of the same large-scale structure of the galaxy. This does not mean they formed together. Stars can be separated by hundreds of light years, and still be part of the same spiral arm. But it does mean that their chemical makeup, their mix of elements heavier than hydrogen and helium, is often similar. They are products of a galaxy that has already gone through many generations of star formation and supernovae, enriching the interstellar medium with heavier elements. This is part of what makes our local region of the Milky Way friendly to planets, and eventually to life. The nearest stars of Sagittarius share that heritage. They are not primordial stars made only of the simplest elements. They are part of a chemically mature galaxy. When you look at one of these stars in Sagittarius, you are looking at a sun that likely formed from material that once passed through earlier stars. The iron in its core, the calcium in its outer layers, all of it was forged in stellar furnaces long before that star itself was born. That idea can give a different flavour to the concept of distance. The nearest stars are not just points in space. They are part of a long chain of cosmic recycling, connected to the same processes that eventually made the atoms in your own body. Of course, not all of the stars you see in Sagittarius are part of this local layer. Many lie far beyond, closer to the galactic centre, but the nearest ones serve as a kind of foreground, a set of reference points that anchor your view. Astronomers sometimes use these nearer stars to calibrate their measurements of more distant ones. By understanding the properties of stars at known distances, they can better interpret the light coming from stars that are much farther away. This calibration process is another quiet, careful step in building a picture of the galaxy. It relies on the nearest stars as a kind of foundation, a baseline against which the deeper structure can be measured. There is also a more personal way to think about these distances. The nearest stars in Sagittarius are, in a sense, part of the same local stellar community as our Sun. They are fellow travellers around the Milky Way, moving along similar orbits, sharing the same general neighbourhood. If you could somehow look down on the galaxy from above, you would see our Sun and these stars as part of a loose, sprawling spiral arm, winding its way around the galactic centre. They are not close together in any tight cluster, but they are part of the same broad structure. This can make the galaxy feel a little less abstract. Instead of a vast anonymous disk of light, it becomes a place with regions and neighbourhoods, with areas that are more familiar and others that are more remote. The nearest stars of Sagittarius belong to the familiar part. They are not visitors from the deep interior of the galaxy. They are local, even if local still means hundreds of light years away. It is also worth noting that distance measurements are not always perfectly precise. Even with modern instruments, there is some uncertainty in how far away a given star is. Parallax measurements have margins of error. Models of stellar brightness and behaviour have assumptions built into them. This means that when astronomers say a star is 140 light years away, or 230 light years away, they are giving a best estimate, not an exact, unchanging number. The true distance might be a little more or a little less, but those uncertainties are small compared to the overall scale. Whether a star is 220 or 240 light years away, it is still unimaginably distant in human terms. This brings us back to the idea of using these nearest stars as a stepping stone into the deeper layers of Sagittarius. They are the first markers along a line of sight that extends far beyond them, through clouds of gas, star clusters, and eventually to the crowded, energetic centre of the Milky Way. In that sense, the nearest stars are like the first hills you see when you look toward a distant mountain range. They are part of the same landscape, but they are not the main event. They hint at what lies beyond without revealing it fully. As you let this idea settle, you might imagine standing on a long, dark road at night. The nearest streetlights illuminate the area around you clearly. Farther down, you see a glow, a suggestion of a town or city in the distance. You cannot see the buildings or the streets, but you know they are there. The nearest stars of Sagittarius are those streetlights. They light up the immediate foreground of a much larger scene. Even the nearest stars in this familiar pattern are far beyond anything we can reach, far beyond anything we can directly touch, and yet close enough, in a cosmic sense, to share our place in the same broad, spiral arm of the galaxy. They are distant, but not remote. They are part of our local patch of the Milky Way, shining quietly across centuries of space and time to mark the front edge of a much deeper, much larger view. Beyond the bright foreground of nearby stars, past the few hundred light-years that mark the familiar edge of our local stellar neighbourhood, the view into Sagittarius begins to stretch into a very different kind of distance. This is where the idea of far stops meaning something you can compare to a road trip, or even a journey across a continent, and starts to mean something that belongs entirely to the scale of a galaxy. Looking in this direction is not like gazing at a wall of stars at a single depth. It is more like looking down a long layered corridor, where each step forward in imagination carries you deeper into the Milky Way itself. The farthest stars associated with Sagittarius are not simply on the other side of the constellation. They are near the heart of the galaxy, tens of thousands of light years away, in a region so crowded and energetic that the very idea of individual isolated stars begins to blur. Let's start by anchoring that distance with something familiar from earlier. The nearest bright stars in Sagittarius sit a few hundred light years away. The centre of the Milky Way, in the same general direction, lies about 26,000 light years from Earth. That is not just a bigger number. It represents a shift in scale that is hard to fully absorb. If you imagine the distance to the nearest stars as a short walk across a town, then the distance to the galactic centre is like crossing an entire continent, not on a map, but in a straight line through the planet itself. The comparison is imperfect, of course, because no earthly distance really prepares you for something that spans a quarter of a galaxy. The stars that lie near this far edge of Sagittarius are not just far from us. They live in a fundamentally different environment. The region around the galactic centre is denser, more active, and more extreme than the relatively calm outskirts where our Sun resides. In our local spiral arm, stars are spaced several light years apart on average. Near the centre, that spacing shrinks. Stars crowd together in clusters and swarms. The gravitational pull of the central black hole and the combined mass of billions of stars shape their motions into fast, tight orbits. The sky from a planet in that region would look nothing like our own. The night might never truly be dark, with stars packed so closely that the space between them glows faintly all the time. So when we talk about the farthest stars in Sagittarius, we're not just talking about distance, we're talking about a different neighbourhood of the galaxy altogether. But how do we know those stars are there, if we cannot see most of them directly? This is where astronomy becomes a quiet exercise in inference. The centre of the Milky Way is hidden from our eyes by thick clouds of dust and gas. Visible light cannot easily pass through these clouds, so the region appears dim, or even completely dark in ordinary telescopes. Instead, astronomers use other forms of light. Infrared radiation, for example, can pass through dust much more easily. Radio waves can travel through it almost unhindered. By observing Sagittarius in these wavelengths, scientists can peer into the heart of the galaxy and map out the stars and structures that lie far beyond what we can see with our eyes alone. These observations reveal a bustling, crowded core. There are dense star clusters, some containing hundreds of thousands of stars packed into regions only a few dozen light years across. There are massive clouds of gas, heated and stirred by intense radiation and strong gravitational forces. There are stars being born and stars dying, sometimes in dramatic explosions that send shockwaves through the surrounding space. At the very centre of it all sits Sagittarius, a star, the supermassive black hole. Its presence is inferred not by seeing it directly, but by watching how nearby stars move. These stars orbit something invisible, something with a mass millions of times that of the Sun, confined to a region smaller than our solar system. Their rapid, looping paths trace out the shape of a deep gravitational well. Those stars circling so close to the black hole are among the farthest members of Sagittarius in any meaningful sense. Their light has been travelling for about 26,000 years to reach us. When you see them, You're seeing them as they were long before the first cities were built, long before the first written stories were recorded. To put that into a gentler perspective, consider what humanity was like 26,000 years ago. Our ancestors were living in small groups, using stone tools, painting on cave walls, and migrating across landscapes shaped by ice ages and shifting climates. The light you receive tonight from those distant stars began its journey when the world was in a completely different chapter of its history. This layering of time adds a quiet depth to the idea of distance. The farthest stars in Sagittarius are not just far away in space, they are far away in time. Another way to sense this scale is to think about how astronomers measure these great distances. Parallax, which works for nearby stars, becomes useless at the scale of the galactic center. The apparent shift is too small to detect, even with the most precise instruments. Instead, scientists rely on a combination of standard candles, stellar motions, and models of the galaxy's structure. Certain types of stars near the galactic center, such as red giants and variable stars, have known properties that allow their distances to be estimated. By measuring how bright they appear and comparing that to how bright they should be, astronomers can calculate how far away they must be. The motions of stars around Sagittarius' star provide another powerful tool. By tracking their orbits, scientists can determine both the mass of the central black hole and the distance to it. This distance then becomes a reference point for mapping the rest of the region. Over time, these measurements have converged on that figure of roughly 26,000 light-years. It is not perfectly exact. Different studies give slightly different numbers, but they all cluster in the same range. The uncertainty is small compared to the vastness of the distance itself. Beyond the galactic center, the Milky Way continues. There are stars on the far side of the galaxy, more than 50,000 light-years away from us. Some of them also lie in the general direction of Sagittarius, though they are even more heavily obscured by dust and gas. In a sense, the farthest stars you can associate with Sagittarius are not just near the center, but on the other side of the galaxy entirely. Their light, if it reaches us at all, has had to pass through the densest, dustiest part of the Milky Way. This makes them extremely faint and difficult to detect. Most of what we know about that far side comes from radio and infrared observations, which can trace gas clouds and star-forming regions, even when individual stars are invisible. So when you look towards Sagittarius, you're not just looking at a single layer of the galaxy. You're looking through it. You're looking across spiral arms, star clusters, dust lanes, and the central bulge, and possibly into the distant outskirts beyond. The depth of this view is what gives Sagittarius such a special role in our understanding of the Milky Way. It is one of the few directions where we can study the structure of the galaxy from the inside, using our own position as a vantage point. Another way to think about the farthest stars is in terms of energy and environment. The region near the galactic center is flooded with radiation from massive stars and energetic events. Supernovae occur more frequently there than in our quieter neighbourhood. The interstellar medium, the mix of gas and dust between stars, is more turbulent and dynamic. Stars that form in this environment grow up under very different conditions. Their formation can be triggered by shock waves from nearby explosions or by the intense gravitational forces of dense clouds. Their lifetimes and behaviours can be shaped by close encounters with other stars, something that is rare in our part of the galaxy. This means that the farthest stars in Sagittarius are not just distant. They are, in a sense, living in a different kind of galaxy, even though it is the same Milky Way. From our perspective, these differences are mostly invisible. We see faint points of light, or sometimes nothing at all. But behind that faintness lies a region of extraordinary activity and complexity. There is also a subtle way in which the farthest stars shape what we see in the foreground. The glow of the Milky Way in Sagittarius, that soft, cloudy band of light, comes largely from the combined light of countless distant stars near the galactic center. They are too faint and too numerous to be seen individually, but together they create a luminous background. So even when you think you're looking at empty space between the brighter foreground stars, you're actually seeing the blended light of faraway suns, their individual identities lost in the crowd. This blending is another reminder that farthest does not always mean separate. The distant stars are part of the same scene, contributing to the overall appearance of the region even when they cannot be picked out one by one. If you could somehow move closer to the galactic centre, the view would change dramatically. The faint glow would resolve into countless individual stars. The dark dust lanes would appear as thick three-dimensional clouds. The central bulge of the galaxy would loom large, filling much of the sky. From that vantage point, our own sun would be just another distant star lost among billions. Thinking about this can quietly flip your sense of perspective. From Earth, Sagittarius feels like a direction towards something distant and unknown. From the galactic centre, Earth would feel like a distant, unremarkable point of light on the outskirts of a vast system. Distance, in this sense, is always relative. The farthest stars for us are the nearest for someone else, if there was someone else to stand there and look back. Another layer to consider is how long these farthest stars will remain where they are. The galaxy is not static. Stars orbit the centre, spiral arms shift and evolve, clouds of gas collapse and disperse. Over millions of years, the stars near the centre will move along their orbits, changing their positions relative to one another and relative to us. The pattern we see today in Sagittarius will not be the pattern seen by future observers. Even the distance to the galactic centre itself is not fixed in a strict sense. Our Sun is orbiting the centre, taking about 225 to 250 million years to complete one full circuit. As it moves, the distance between us and the centre changes slightly. It is a slow, gentle dance on a timescale far beyond human history. This motion adds another quiet dimension to the idea of farthest. The stars near the centre are not permanently far in a fixed geometric way. They are part of a dynamic system, and our relationship to them is constantly, if slowly, evolving. There's also the role of dark matter to consider. The Milky Way is surrounded by a vast halo of invisible mass that extends far beyond the visible disk of stars. This dark matter does not emit or absorb light, but its gravity influences the motion of stars throughout the galaxy. The farthest stars in Sagittarius, especially those near and beyond the centre, are moving within this combined gravitational field. Their orbits and velocities carry information about the distribution of this unseen mass. So when astronomers study the motions of stars in Sagittarius, they are not just mapping visible objects. They are probing the structure of something that cannot be seen at all, a vast invisible framework that holds the galaxy together. From a human point of view, this adds a certain quiet mystery to the idea of distance. The farther you look, the more you encounter things that cannot be directly observed, only inferred. Yet, despite all of this complexity, the experience of looking at Sagittarius from Earth remains simple. You see a pattern of stars, a bright region of the Milky Way, perhaps a familiar teapot shape. You do not see the black hole, the dense clusters, the dark matter, or the far side of the galaxy. Those things exist in the same direction, in the same line of sight, but they are hidden behind layers of dust, light, and time. This contrast between what is there and what is visible is part of what makes the farthest stars feel so distant. Not just physically, but conceptually. They are present in the data, in the models, in the careful measurements of astronomers, but not in the immediate sensory experience of stargazing, and yet their influence is felt. They shape the glow of the Milky Way. They define the centre around which our entire galaxy turns. They anchor our understanding of where we are in the cosmic landscape. If you let your thoughts drift along that line of sight, from the nearest stars a few hundred light years away, past clouds of gas and dust, through star clusters and dense fields of light, all the way to the galactic centre and beyond, you begin to trace a path that spans a significant fraction of the Milky Way's entire diameter. That path is what gives Sagittarius its true, quiet enormity. Not because the pattern itself is physically connected, but because it points across such a vast and complex stretch of space. From the moment you first learn to look up and recognize a few familiar shapes among the stars, a quiet assumption often settles in without being invited. The stars that look close together must be close together. The shapes that look small must be small. The ones that stretch wide across the sky must be enormous. It feels intuitive, almost obvious. And yet, the night sky is one of the best places to discover how easily the mind can be guided by appearances into believing something that is only partly true. When you look at Sagittarius or any constellation, what you're really seeing is not size in the way you would see the size of a tree or a building. You're seeing angle. You're seeing how much of your field of view is taken up by a pattern of light that exists at many different distances all at once. That difference between angle and actual physical extent is where the illusion of size quietly lives. To get a sense of this, it can help to think about something simple and familiar. Imagine standing on a long straight road. Far away in the distance you see a large mountain. Closer to you, perhaps only a few meters away, stands a small signpost. If you line them up just right, the signpost can completely cover the mountain from your point of view. The mountain is unimaginably larger than the sign, but because it is so far away, it takes up a much smaller angle in your vision. The same principle works in the sky, but on a scale so vast that the brain has trouble keeping track of it. The moon, for example, looks about the same size in the sky as the sun. You can hold up a coin at arm's length and cover either one, but in reality the sun is about 400 times wider than the moon. The reason they appear the same size is that the sun is also about 400 times farther away. The geometry lines up in a way that creates a perfect visual coincidence. Once you start noticing this, the sky becomes a place full of these quiet tricks. A star that looks bright and prominent might be relatively close and modest in size, or it might be incredibly large and very far away. A patch of sky that feels small and contained might actually represent a vast volume of space stretching deep into the galaxy. Sagittarius is a particularly good example of this because it combines both a wide angular spread and an enormous range of distances. If you measure how much of the sky Sagittarius covers using angular size, it is one of the larger constellations. Its official boundaries, defined by astronomers, cover a region of sky that spans hundreds of square degrees. If you were to map it out, it would take up a noticeable chunk of the celestial sphere. From Earth, that can make Sagittarius feel big in a very immediate visual sense. It stretches across a wide area. You might have to move your gaze or turn your head to take it all in. But that visual bigness does not directly tell you how physically large the region is in space. At the same time, Sagittarius points toward one of the deepest lines of sight into the Milky Way. The stars you see in that region are not all sitting on a flat plane at a similar distance. They are scattered along a corridor that stretches tens of thousands of light years. So here is where the illusion begins to layer itself. You have a region of sky that looks wide, and behind it, a region of space that is incredibly deep. The two combine to create a sense of enormity that is both real and misleading, depending on how you interpret it. Consider another constellation for comparison, one that points away from the galactic center, toward the outer edge of the Milky Way, or even out into intergalactic space. Such a constellation might cover a similar angular area in the sky. It might look just as wide, but behind it, the density of stars drops off. There is less depth, less structure, fewer layers. Visually, the two might feel similar in size. Physically, the regions they point toward are very different. This is one of the subtle ways the sky can mislead. Our eyes are excellent at judging angles and patterns, but they are not equipped to judge depth on a galactic scale. Everything beyond a certain distance collapses into the same flat surface in our perception. Even the idea of behind starts to lose its meaning. When you look at Sagittarius, you might imagine the bright stars as being in front of the Milky Way, and the Milky Way as a background. In a sense, that is true. But behind that background are more stars, and behind those more structure, and beyond that, the far side of the galaxy. There is no final backdrop, the depth keeps going. Another way the illusion of size shows up is in how we interpret brightness. A bright star often feels closer, larger, or more important than a faint one. And sometimes that is true. Some of the brightest stars in Sagittarius are relatively close and physically large. But in other cases, a faint star might be far more massive or luminous than a bright one, just much farther away. Its light has spread out across so much space that only a small fraction of it reaches your eyes. So the sky quietly mixes together size, distance, and brightness into a single visual experience that does not easily separate into its components. This blending can make it hard to develop an intuitive sense of scale. When everything looks like a point of light, it is difficult to remember that those points represent objects that range from small red dwarfs to giant stars hundreds of times larger than our Sun, from neighbours a few hundred light years away to distant suns near the centre of the galaxy. Another layer of the illusion comes from how the sky itself is presented to us. We often think of it as a dome, a curved surface arching overhead. This mental model is helpful for navigation and storytelling, but it reinforces the idea that everything in the sky is roughly the same distance away, attached to that dome. In reality, there is no dome. There is just space, extending outward in all directions, filled with objects at vastly different depths. Sagittarius, because it lies along the plane of the Milky Way, often appears embedded in a glowing band of light. That band can feel like a backdrop, like a painted strip behind the brighter stars. But that backdrop is actually made up of countless distant stars, each one a sun in its own right. So in a way, the illusion of size in Sagittarius is not just about how wide it looks, it is also about how the background itself is an object, or rather a vast collection of objects that we mentally flatten into a single layer. The Milky Way is often described as a river of light, a cloud, or a mist. Those metaphors capture the visual experience, but they hide the physical reality. That soft glow is the combined light of stars spread across thousands of light years. If you could step closer, that glow would break apart into individual points, and those points would be separated by immense distances. There is also the way our own bodies and senses shape the experience. The human eye is more sensitive to brightness than to colour in low light. At night, our vision shifts into a mode that favours detecting light over distinguishing fine detail. This is why stars often appear white or pale, even though many of them have distinct colours. This limitation smooths out the sky, reducing its complexity and reinforcing the impression of a simple pattern. The richness of depth and variation becomes harder to see, and the illusion of a flat, evenly distant surface becomes stronger. Technology can disrupt this illusion. A telescope or a long-exposure photograph can reveal layers of stars, clouds of gas, and structures that are invisible to the naked eye. When you see such an image of Sagittarius, the region often looks crowded, chaotic, and deep. Nothing like the simple teapot shape you might recognise in the sky. But even those images can create their own illusions. A photograph might show a nebula glowing brightly in colour, filling the frame. They can feel close, almost touchable. But that glowing cloud might be thousands of light years away and dozens of light years across. The brain, seeing a detailed image, tends to interpret it as something near and tangible, even when the caption says otherwise. Another quiet trick of perception comes from how the sky moves. Over the course of a night, Sagittarius rises, arcs across the sky and sets. That motion is smooth and steady, and it can give the impression that the constellation itself is moving as a single coherent thing. In reality, the stars in Sagittarius are not moving together in that way. The motion you see is entirely due to Earth's rotation. Each star has its own path through space, its own orbit around the galactic centre. They are only temporarily grouped in your field of view by the spin of the planet beneath you. This can reinforce the sense that Sagittarius is an object, something that travels as a unit across the sky. The illusion of size is tied to the illusion of unity. There is also a temporal aspect to this. The sky you see tonight is not the sky as it exists now, in a universal sense. It is a mix of different moments in the past. The nearest stars in Sagittarius are being seen as they were a few hundred years ago. The distant ones near the galactic centre are being seen as they were tens of thousands of years ago. So when you look at the full region, you're not just seeing a wide area of space, you're seeing a wide span of time layered into a single visual scene. This can subtly affect how size feels. Something that stretches across both great distances and great times can feel more vast, even if the actual angular area it covers in the sky is not particularly large. Another comparison can help here. Think about looking at a long row of streetlights at night. The nearest ones are bright and clear. The farther ones fade into the distance, becoming smaller and dimmer until they blur into a line of light. From your point of view, that line might not take up much of your field of vision. It might be a narrow band stretching away. But you know, if you were to walk along it, that it would take you a long time to reach the end. Sagittarius is like that line of streetlights, except that instead of a road, it traces a path through the galaxy, and instead of kilometers, the distances are measured in light years. The illusion of size also shows up in how we compare constellations to one another. Some constellations are physically compact in the sense that many of their stars are part of the same cluster or association. Others, like Sagittarius, are physically spread out, with stars at many different depths. Visually, both types can look similar in size. A compact cluster might appear as a small, tight group. A spread-out constellation might appear as a loose, wide pattern. But those appearances do not directly reflect the true volume of space involved. In fact, a visually small cluster might occupy a much smaller volume of space than a visually wide but shallow region of the sky. Or the opposite might be true. The only way to know is to measure distances, and even then the result is often a range rather than a single value. This is why astronomers tend to talk about specific objects rather than constellations when discussing physical size. A star cluster can have a radius measured in light years. A nebula can be described as being tens of light years across. A galaxy can be measured in tens or hundreds of thousands of light years. A constellation, by contrast, is a patch of sky, a direction, not a single thing. Its size depends on what you choose to include. Do you include only the stars that make up the traditional pattern? Do you include all the stars within the official boundaries? Do you include the distant structures in the same line of sight, like the galactic centre and the star clouds beyond it? Each choice leads to a different answer, and each answer highlights a different aspect of the illusion. There is also a more personal dimension to this. The size of the sky itself can feel different depending on where you are and how you are feeling. On a clear, dark night in a wide open place, the sky can feel enormous, almost overwhelming. In a city hemmed in by buildings and lights, it can feel small, distant and flat. Sagittarius, in those two settings, can feel like two different things. In one, it might be a faint, barely noticeable shape. In the other, it might be a rich, glowing region that draws your attention again and again. The physical reality of the stars has not changed, but your experience of their size has. This connection between perception and scale is part of what makes astronomy a quietly philosophical pursuit. It invites you to notice not just what is out there, but how you are seeing it, and how much of that seeing is shaped by your own position, tools, and expectations. When you step back and consider all of this, the question, how big is Sagittarius, starts to feel less like a request for a number and more like an invitation to explore layers of meaning. It is big in the sense that it covers a wide area of sky. It is big in the sense that it points toward the deep interior of the Milky Way. It is big in the sense that it spans a huge range of distances and times, and it is also, in a visual sense, just a handful of stars you can trace with your finger. All of those things are true at once. The illusion of size, then, is not something to be corrected or dismissed. It is something to be understood and appreciated. It shows how a simple, immediate experience, looking up at a pattern of lights, can connect to something vast and complex, stretching far beyond what the senses alone can grasp. As you let that idea settle, you might find that the sky feels a little deeper, a little more layered, even if nothing about the view itself has changed. Along the wide, pale band of the Milky Way, where the sky seems to thicken with light and shadow, Sagittarius occupies a place that feels less like a single region, and more like a bridge. It is not merely a pattern of stars set against the galaxy. It is a direction that cuts through it, a line of sight that travels from the quieter outskirts where our sun drifts, inward toward the crowded, glowing core where the Milky Way gathers itself most tightly. Thinking about Sagittarius this way begins to change how its size feels. Instead of imagining it as a flat shape spread across the sky, you can start to imagine it as a long, stretched pathway, extending through the galaxy's disk like a thread pulled through layers of fabric. The length of that thread is not measured in degrees or angles, but in thousands and tens of thousands of light years. Our solar system sits in one of the Milky Way's spiral arms, a region sometimes called the Orion Arm or Orion Spur. It is not a major arm like the grand, sweeping ones you see in pictures of other spiral galaxies, but a smaller branch between two larger arms. From here, the galaxy extends in all directions, but not evenly. In some directions you look outward toward the thinner, quieter edge of the disk. In others you look inward toward the thick, dense centre. Sagittarius is one of those inward-looking directions. If you could hover far above the galaxy and look down on it, you would see the Milky Way as a vast, flattened spiral, with arms winding around a bright, swollen central bulge. From our position, Sagittarius points roughly toward that bulge. It is not a perfectly straight shot to the exact centre, but it comes close enough that much of what you see in that region of sky is influenced by the galaxy's core. This means that when you look at Sagittarius, you're looking across a large fraction of the Milky Way's radius. The galaxy is about 100,000 light-years across from one edge of the disk to the other. The distance from our Sun to the centre is about 26,000 light-years. So that line of sight covers more than a quarter of the galaxy's diameter, and if you extend it beyond the centre, potentially much more. That alone gives Sagittarius a kind of stretched, elongated presence that is not obvious from its appearance in the sky. The width of the pattern you see might span a few degrees of angle, but the depth it represents spans a significant portion of an entire galaxy. This depth is not uniform. It is layered with structure. The first layer, closest to us, consists of stars in our local spiral arm, the ones a few hundred light-years away that form much of the recognizable pattern. These stars are moving along with the Sun, orbiting the galactic centre at roughly the same distance, embedded in similar conditions of gas, dust and radiation. Beyond that lies the next layer, the inner spiral arms. The Milky Way structure is not a simple, smooth disk. Its arms are regions of higher density, where gas and dust collect and star formation is more active. As your line of sight passes through these arms, you encounter more clusters of young stars, more glowing nebulae, and more dense clouds that block and scatter light. These spiral arms are not rigid structures. They are more like traffic jams in the flow of stars and gas, regions where material piled up as it moves around the galaxy. Stars form there, shine for millions or billions of years, and then drift onward, leaving the arm behind. Sagittarius points through at least one of these inner arms, adding to the richness and complexity of what lies in that direction. Then, closer to the centre, the structure changes again. The galaxy's disk thickens into a central bulge, a roughly spherical region packed with stars. This bulge is older, on average, than the spiral arms. Many of its stars formed early in the galaxy's history and have been orbiting the centre for billions of years. The density here is much higher than in our local neighbourhood. Stars pass much closer to one another. The sky from a planet in this region would be filled with light, not just from a few bright stars, but from a sea of them. Behind all of this, beyond the bulge, the galaxy extends into its far side, with more spiral arms and more layers of stars, gas and dust. Most of that is hidden from our view by the material in the foreground, but it is still there, contributing to the gravitational balance of the whole system. So when you think about stretching Sagittarius across the Milky Way, you're really thinking about this entire sequence of regions, from our quiet arm through inner arms, into the bulge, and possibly beyond. This stretch is not something you can see directly. The dust between the stars acts like a veil, especially in visible light. It absorbs and scatters photons, turning bright regions dim and hiding entire swathes of the galaxy behind dark lanes. But even that veil tells a story. The very fact that Sagittarius appears streaked with dark patches and glowing clouds is a sign of how much material lies along that line of sight. Those dust lanes are part of the same spiral arms and clouds that make up the galaxy's structure. If you look at images of Sagittarius taken in infrared light, much of that darkness disappears. The Milky Way in that direction suddenly looks brighter and more continuous. The bulge stands out as a glowing mass. The star fields become denser. The sense of depth becomes more pronounced. Radio images go even further, revealing the distribution of hydrogen gas, the most abundant element in the galaxy. These maps show how the gas forms vast, sweeping structures that trace the spiral arms and wrap around the central bulge. Together, these different views create a multi-layered picture of what Sagittarius really represents. It is not a slice of empty space with a few stars sprinkled in. It is a thick cross-section of a galaxy. Another way to stretch this idea is to think about how long it takes to move through these regions. If you could travel at the speed of light, it would take you 26,000 years to reach the centre of the Milky Way from Earth. If you continued on to the far side of the disk, it might take another 20,000 to 30,000 years, depending on the path you took. That means a journey through Sagittarius, from our position to the far edge of the galaxy, would span a time longer than all of recorded human history, many times over. And yet, all of that distance is compressed into a small patch of sky that you can cover with your hand. This compression is part of what makes the night sky so deceptive and so fascinating at the same time. It takes something that is truly enormous and presents it as something manageable, something you can point at and say, there. There is also the role of motion to consider. The Milky Way is not a static backdrop. Everything in it is moving. The sun is orbiting the centre. The stars in Sagittarius are orbiting too, each at their own speed and along their own path. The spiral arms themselves are patterns of motion rather than fixed structures. Gas flows into them, forms stars, and then flows out again. Over millions of years, the arms shift and change. So the stretch of Sagittarius across the Milky Way is not a frozen snapshot. It is a dynamic, evolving corridor. The stars you see now in that direction will not always be there in the same configuration. New stars will form, old ones will die, clouds will collapse and disperse. If you could watch the galaxy and fast forward over hundreds of millions of years, the line of sight that defines Sagittarius would sweep across different structures. The central bulge would remain, but the details around it would change. This dynamic nature adds another layer to the idea of size. Sagittarius is not just large in space, it is large in time. It represents a region of the galaxy that is constantly being reshaped. There is also a gravitational story embedded in this stretch. The closer you get to the galactic centre, the stronger the gravitational pull becomes. Stars move faster, orbits become tighter. In the innermost region near Sagittarius, A star, Stars whip around the black hole at incredible speeds. Some complete full orbits in just a few decades. Their paths are tracked carefully by astronomers, providing some of the clearest evidence for the existence and mass of the black hole. Those stars are part of the same stretched line of sight that begins with the nearest foreground stars in Sagittarius. They're connected, not by physical proximity, but by the direction you are looking. This connection can make the region feel like a continuous thread, running from the calm, spacious outskirts of the galaxy into its most intense and energetic core. It is also worth thinking about what lies above and below this stretch. The Milky Way is not an infinitely thin disk, it has thickness. Stars and gas extend above and below the plane of the galaxy, forming a kind of halo around the disk. Some of the stars you see in Sagittarius might belong to this thicker disk, or even to the galactic halo, passing through the region on orbits that take them far above and below the main plane. So even within that stretched corridor, there is vertical structure as well as horizontal. The region is not just long, it is deep and tall, a three-dimensional volume of space. All of this complexity sits behind the simple outline of a constellation. If you imagine taking a knife and slicing through the Milky Way along the direction of Sagittarius, you would cut through layers of stars, gas and dust, each with its own properties and history. The slice would be thick near the centre, thinner in the arms, and surrounded by a faint halo of stars and dark matter. That slice would be a kind of cosmic cross-section, showing how the galaxy is built from the inside out. This is why Sagittarius is so valuable to astronomers. It is one of the few places where we can study the structure of the Milky Way in detail, not by looking at it from the outside, but by looking through it from within. We cannot step back and take a picture of our galaxy the way we can with distant ones. We have to piece together its shape and size from the inside, using lines of sight like this one. Sagittarius, with its deep reach into the galactic centre, provides a particularly rich set of clues. There is also a poetic but grounded way to think about this stretch. The light from the farthest stars in Sagittarius began its journey long before our species existed. It has travelled across spiral arms, through clouds of dust, past countless other stars, and through the gravitational field of the galaxy itself, before finally reaching Earth. In that sense, every glance in this direction is a kind of long-distance communication, a message sent across tens of thousands of years and received in a fraction of a second by your eyes. The region is stretched not just across space, but across time and history. As you sit with that idea, the sky can start to feel less like a ceiling and more like a landscape you're embedded within, a vast structure you're moving through rather than simply observing from below. And this brings us back to the question of size. If you measure Sagittarius by its width in the sky, it is a handful of degrees. If you measure it by the depth of the galaxy it points toward, it is tens of thousands of light years. If you measure it by the span of time its light represents, it reaches back tens of thousands of years into the past. All of these measurements are valid, depending on what you're interested in. None of them alone captures the whole picture. Stretching Sagittarius across the Milky Way, then, is not just about mapping a region of space. It is about connecting different scales, from the small and local to the vast and galactic, from the immediate and visible to the distant and hidden. Somewhere along that long, crowded line of sight that Sagittarius opens into the Milky Way, there is a place that does not announce itself with brightness or colour, even though it holds more influence over the galaxy than almost anything else within it. You cannot point to it easily with your eyes. You cannot trace its outline with your finger against the sky. And yet, this hidden region shapes the motion of billions of stars, including our own sun, in a slow, steady dance around a centre that is felt far more than it is seen. The galactic centre is not a glowing beacon or a dramatic swirl of light the way it is sometimes imagined in artwork. From Earth, invisible light, it is almost entirely concealed. Thick clouds of interstellar dust lie between us and the core of the Milky Way, blocking and scattering the light that would otherwise reveal it. What reaches your eyes instead is a patchwork of brighter stars in the foreground, crossed by dark lanes and soft glows that hint at something more behind them. So when we say the galactic centre hides in Sagittarius, we mean that quite literally. It is there, in that direction, but it does not show itself plainly. It sits behind layers of material that act like a curtain drawn across the heart of the galaxy. To understand where this place is, it helps to imagine the Milky Way as a wide, flattened disk with a swollen, rounded bulge in the middle. Our Sun sits off to one side, about 26,000 light-years from that bulge. From our vantage point inside the disk, we look toward the centre through the plane of the galaxy, where most of the stars, gas and dust are concentrated. This is very different from looking at a distant galaxy from the outside. When astronomers photograph other spiral galaxies, they can see the bright centre clearly, surrounded by sweeping arms. But we do not have that luxury with our own. We're embedded within it, peering through its thickest, most crowded region to find its core. That is why Sagittarius plays such an important role. It marks the general direction of the centre, even if the centre itself remains invisible in ordinary light. If you could somehow turn off all the dust between here and there, the view would be extraordinary. The central bulge of the Milky Way would fill a large portion of the sky, a dense, glowing mass of stars packed together far more tightly than in our local neighbourhood. The night would be bright, not just with a few prominent stars, but with a continuous luminous backdrop of countless suns. But the universe has not given us a clear window. Instead, it has given us a layered, filtered view that requires a different kind of seeing. Infrared light provides one of those ways in. Because its wavelengths are longer than those of visible light, it can pass through dust more easily. When astronomers look towards Sagittarius in the infrared, the dark lanes soften and the glow of the central bulge begins to emerge. In these images, the Milky Way's core appears as a broad, bright region, thick with stars. You can see clusters that are invisible in optical images. You can trace the structure of the bulge and the inner spiral arms more clearly. The sense of depth and density becomes much more pronounced. Radio waves offer another perspective. Hydrogen, the most abundant element in the galaxy, emits radio signals at a specific wavelength. By mapping this emission, astronomers can trace vast clouds of gas, even in regions completely hidden by dust in visible light. These maps reveal the skeleton of the galaxy's structure, showing where gas piles up in spiral arms and around the central bulge. Through these different forms of light, the hidden centre of the Milky Way gradually comes into focus, not as a single picture, but as a layered understanding built from many pieces of information. At the very heart of this region lies Sagittarius, a star, the supermassive black hole. It is not a dramatic, constantly devouring monster in the way popular imagination often portrays black holes. Most of the time, it is relatively quiet, slowly drawing in small amounts of gas and dust from its surroundings. Its presence is revealed not by a bright glow, but by the motion of stars around it. In the last few decades, astronomers have tracked the orbits of individual stars near the galactic centre with remarkable precision. These stars move in fast, tight loops, circling something they cannot see. By measuring the speed and shape of these orbits, scientists can calculate how much mass must be concentrated in that tiny region of space. The answer comes out to about 4 million times the mass of our Sun, confined to a volume smaller than our solar system. There is no known object other than a black hole that can explain that combination of mass and compactness. So even though Sagittarius A star is hidden from view, its influence is unmistakable. It is the anchor point around which the inner galaxy revolves. This hidden centre also helps explain why the region around Sagittarius feels so rich and complex. The gravitational pull of the core shapes the motion of stars and gas throughout the inner Milky Way. It contributes to the way spiral arms form and persist. It helps drive the flow of material inward and outward, fueling star formation and shaping the overall structure of the galaxy. In that sense, when you look towards Sagittarius, you are looking toward the engine room of the Milky Way, even if you cannot see the machinery directly. There is something quietly intriguing about the fact that such an important place can be so well concealed. It challenges the idea that the most powerful or significant things must always be the most visible. In the galaxy, as in many other contexts, influence does not always come with brightness. The hidden nature of the centre also means that much of what we know about it has been discovered only recently in historical terms. For most of human history, the galactic core was just another dense patch of stars in the Milky Way with no special significance attached to it. It was not until the development of radio astronomy and infrared detectors in the 20th century that scientists began to piece together a clearer picture of what lay behind the dust. The idea of a supermassive black hole at the centre of our galaxy is only a few decades old. This adds a subtle layer of novelty to the region. Even though the stars there are ancient, our understanding of them is relatively new. Sagittarius in this sense is a gateway not just to a distant part of the galaxy, but to a frontier of human knowledge that is still being actively explored. Another aspect of the hidden centre is how it affects what we see in the surrounding sky. The dense star fields and bright nebulae in Sagittarius are not random. They are part of the galaxy's inner structure, shaped by the same forces that dominate the core. Star formation is more active in the inner regions of the Milky Way than in the outskirts. There is more gas available, more compression from spiral arms and gravitational interactions, and more energetic events like supernova that can trigger the collapse of clouds into new stars. This is why Sagittarius is home to so many prominent nebulae and clusters. These are visible signs of the ongoing life of the galaxy, concentrated along a line of sight that leads inward. At the same time, the hidden centre also creates the dark features you see. The dust that blocks the light of the bulge and the far side of the galaxy is part of the same material that will eventually form new stars. The dark lanes are not empty. They are full of potential. If you imagine the galaxy as a living system, Sagittarius points toward a region where that system is most active, most dynamic, and most influential. Another way to think about where the galactic centre hides is to consider how small it appears from our vantage point, even though it is such a dominant feature. The central bulge of the Milky Way is about 10,000 light-years across. That is enormous in physical terms. But from 26,000 light-years away it spans only a few degrees of sky. It fits comfortably within the broader region of Sagittarius. So even if the dust were not there, the centre would not fill the entire sky. It would appear as a bright, dense area, not as an overwhelming presence. Its true significance would still have to be inferred from its effects rather than its appearance. This is another example of how perspective shapes experience. Something can be physically massive and influential, yet visually modest from a particular point of view. The idea of the centre hiding also extends beyond just dust and distance. There is a sense in which the core of the galaxy is conceptually hidden as well. Much of what happens there takes place under conditions that are difficult to replicate or fully understand. The environment near a supermassive black hole is extreme. Gravity is strong, speeds are high, magnetic fields and radiation play complex roles. Even with modern telescopes and sophisticated models, there are still many unanswered questions about how matter behaves in such conditions, how black holes interact with their surroundings, and how these processes influence the evolution of the galaxy as a whole. So when you look towards Sagittarius, you are not just looking toward a distant place. You are looking toward a set of mysteries that science is still working to unravel. There is also a quieter, more subtle way in which the galactic centre hides in everyday stargazing. Most people who look up at Sagittarius are not aware that they are looking toward the heart of the Milky Way. They see a pattern, maybe a teapot shape, maybe just a dense patch of stars, and move on. The knowledge that this direction leads to a supermassive black hole and a dense, ancient bulge of stars is something you have to learn, not something the sky announces on its own. That gap between what is seen and what is known is part of what makes astronomy such a layered experience. The same view can be simple or profound depending on how much context you bring to it. Another detail worth considering is how the position of the galactic centre has been defined. Astronomers have pinpointed its location in the sky with great precision using radio observations of Sagittarius A star. It lies near the border between Sagittarius and the neighbouring constellation Scorpius. So even the name Sagittarius as the marker of the centre is a bit of a simplification. The core of the galaxy does not sit neatly in the middle of the arch's outline. It sits near the edge of the traditional pattern, in a region that our cultural map of the sky has divided between two figures. This is another reminder that the constellations are human constructs laid over a much more complex and continuous reality. The fact that the galactic centre lies near this border also means that the region of the sky associated with it includes stars from more than one named constellation. The direction is what matters, not the label. In that sense, the centre hides not just behind dust, but behind our own naming systems and mental maps. There is also the role of motion to consider. The centre of the galaxy is not a fixed point in an absolute sense. The entire Milky Way is moving through space as part of the local group of galaxies. It is drifting toward a future encounter with the Andromeda Galaxy, a collision that will take place billions of years from now. So the hidden centre is part of a larger motion, a galaxy on a long, slow journey through the universe. The stars you see in Sagittarius are not just orbiting the core. The core itself is moving through intergalactic space. This adds yet another layer to the idea of where the centre is. It is a place within a structure that is itself in motion, within a universe that is expanding. At a human scale, all of this movement is imperceptible. The sky feels stable. The patterns feel fixed. But on cosmic timescales, everything is in flux. If you imagine a future far beyond any human lifetime, the Milky Way will look very different. Its spiral arms will shift. Its star population will change. Its centre may grow as it absorbs more mass. And eventually it will merge with Andromeda to form a new, larger galaxy. The hidden centre of Sagittarius will then be part of a new, combined core, with a different structure and different surroundings. Thinking about this can make the present moment of stargazing feel like a snapshot in a very long story. Another perspective on the hidden centre comes from considering how it affects our own solar system. The Sun's orbit around the galactic centre is slow and steady, taking hundreds of millions of years to complete a full circle. As it travels, it passes through different regions of the galaxy, some denser, some more sparse. These changes can influence the environment of the solar system in subtle ways, affecting the flow of cosmic rays and the gravitational influences of nearby stars. So even though the centre is far away, it still plays a role in shaping the conditions of our own local space over long periods of time. In this way, Sagittarius points not just to a distant, abstract place, but to something that is connected in a broad gravitational sense to our own existence. There is a quiet elegance in the idea that a region of the sky that looks like a simple pattern of stars is actually aligned with the core of a galaxy, a place of immense mass and influence. The fact that this core is hidden adds to that elegance. It suggests that the most important parts of a system are not always the most obvious. As you let these thoughts settle, you might find that looking towards Sagittarius feels a little different. The dark lanes and bright patches are no longer just visual features. They become hints, traces of something deeper behind them. The sky becomes less like a picture and more like a layered story, with a foreground, a middle ground, and a background that stretches far beyond what you can see. And as that sense of depth grows, it naturally leads into a broader comparison. If Sagittarius points towards such a dense and influential region, what about the other constellations? What directions do they open up, and how do their lines of sight differ in terms of depth, density, and structure? Placed side by side in the sky, constellations can feel like a collection of neighbouring pictures, each occupying its own patch of darkness, each offering a different mood, a different texture, a different kind of quiet presence. But when you begin to compare them not just by how they look, but by what lies behind them, the differences become far more than cosmetic. Sagittarius, with its deep reach into the Milky Way's core, starts to stand out as something more like a window than a frame, a direction that opens into layers of structure rather than a simple pattern of stars. To begin this comparison, it helps to think about what most constellations actually represent in physical terms. Many of them are defined by stars that are relatively close to one another in space, at least compared to the distances that stretch toward the galactic centre. These stars often belong to the same general region of the galaxy, sometimes even to the same stellar association or moving group. Take a constellation like the Big Dipper, which is part of Ursa Major. Several of its stars are part of a loose group that form together and still share similar motions through space. They are spread out over a few hundred light years, which is vast by everyday standards but modest on a galactic scale. When you look at that familiar shape, you're seeing something that has a certain physical coherence, even if it is not a tight gravitationally bound cluster. Or consider Orion, another well-known pattern. Many of its brightest stars are part of a large star-forming region, the Orion complex, which includes nebula, young stars, and associations spread across a few hundred light years. Orion feels rich and active because it actually is, in a physical sense. It marks a region of recent and ongoing star birth in our local part of the Milky Way. Now contrast that with Sagittarius. The stars that define its pattern do not belong to a single group or region in the same way. They are a foreground layer, a set of signposts scattered across our local spiral arm. Behind them lies a deep, crowded line of sight that extends through multiple spiral arms into the central bulge of the galaxy and possibly beyond. So while Orion or Ursa Major might represent a region of space that is a few hundred light years deep, Sagittarius represents a region that is tens of thousands of light years deep. That difference in depth is one of the most important ways it sets itself apart. Another way to compare constellations is by considering what direction they point relative to the structure of the Milky Way. The galaxy is not symmetrical from our point of view. In some directions you look outward, away from the centre, toward the thinner, quieter outskirts of the disk. In others, you look inward, toward the dense, luminous core. Constellations like Taurus or Perseus lie along directions that skim across our local spiral arm or look outward toward less crowded regions. When you look there, the background of the Milky Way is often fainter. The sky feels darker, more open, with fewer layers of stars behind the foreground pattern. Sagittarius, by contrast, points inward. The background there is thick with starlight, even when much of it is hidden by dust. The region feels heavy with presence, full of hints that there is more beyond what you can see. This inward versus outward distinction can subtly change the emotional tone of a constellation. Outward-looking regions can feel expansive and open, as though you are gazing into a vast empty space beyond the galaxy. Inward-looking regions can feel crowded and rich, as though you're peering into a busy, complex interior. Neither is inherently more correct or more important, but they offer different experiences of the same galaxy. Another layer of comparison comes from how constellations relate to the Milky Way's plane. Some sit well above or below it, in regions of the sky where the band of the galaxy is faint or absent. In these areas, the stars you see are often part of the galactic halo or the thicker disk, and the background is relatively sparse. Others, like Sagittarius, sit right on the plane of the Milky Way, where the density of stars and gas is highest. Here, the sky feels textured and layered, even to the naked eye. This placement can dramatically affect how a constellation looks and feels. A pattern of stars against a dark, empty background stands out sharply, clean and simple. The same pattern against a glowing band of starlight can feel busy, embedded, almost lost in the richness around it. So when you compare Sagittarius to a constellation that lies far from the Milky Way's plane, you're also comparing two very different kinds of cosmic environments. There's also the matter of physical scale to consider. Some constellations include large, physically connected structures. The Orion Nebula, for example, is a star-forming cloud tens of light years across. The Pleiades cluster in Taurus is a group of stars that form together and still travel through space as a loose family, spanning a few dozen light years. These are objects you can meaningfully measure in physical terms. You can say how wide they are, how massive they are, how long they have existed. Sagittarius, as a constellation, does not contain a single object that defines its physical size in the same way. It contains many objects, spread across a huge range of distances and scales, from nearby giant stars to distant clusters near the galactic centre. So when you ask how big Sagittarius is, you are asking a different kind of question than when you ask how big the Orion Nebula is. You're not measuring a thing, you're measuring a direction. Another interesting comparison comes from looking at how constellations change over time. All of them are subject to the slow motion of stars through the galaxy, but the effect is more noticeable in some than in others. Constellations made up mostly of nearby stars will change shape more quickly, because those stars have larger apparent motions across the sky. Over tens of thousands of years, their patterns can distort significantly. Sagittarius includes some nearby stars, but much of its visual richness comes from distant ones that move more slowly in apparent terms. This can give the region a sense of stability, even though, in reality, everything within it is in motion. This means that the pattern of Sagittarius as a whole may change more subtly over long timescales than some constellations dominated by closer stars. There is also the role of human culture in shaping how we compare constellations. Some have become iconic, deeply embedded in stories, calendars, and navigation traditions. Orion, for example, has been recognized and named in many cultures around the world, often with similar interpretations. Sagittarius also has a long cultural history, but its role is often tied to the zodiac, to astrology, and to seasonal markers. This can give it a different kind of presence in human thought, one that is less about a specific story and more about a position in a larger cycle. When you compare Sagittarius to a constellation like Scorpius, which lies right next to it in the sky, the difference can be subtle but noticeable. Scorpius is defined by a bright curving line of stars that form a clear striking shape. It feels bold and self-contained. Sagittarius, by contrast, feels more diffuse. Its pattern is less obvious unless you know what to look for. The region around it often draws more attention than the outline itself. This difference reflects their physical context. Scorpius's brightest stars are relatively nearby and stand out sharply against the background. Sagittarius's brightest stars are part of a richer, deeper field that can make them blend into the surrounding glow. Another comparison that can be revealing is with constellations in the opposite direction of the sky, those that point away from the galactic centre, toward the outer disk or even out of the galaxy entirely. In those directions, the Milky Way thins out. The number of stars drops. The background becomes darker. If you look far enough away from the galactic plane, you can even begin to see distant galaxies, faint smudges of light millions of light years away. Sagittarius, by contrast, rarely offers that kind of view. The dense foreground of stars and dust blocks the sight of anything beyond the Milky Way. The region is so crowded that distant galaxies are hidden behind the glow of our own. So in a way, Sagittarius is inward-looking. It keeps your attention focused on the structure of the Milky Way itself, rather than letting your gaze wander out into the wider universe. This inward focus gives it a unique role in understanding our place in the cosmos. When you look at a distant galaxy, you're seeing another system from the outside. When you look at Sagittarius, you're seeing your own system from the inside. Comparing those two experiences can be quietly profound. One shows you how galaxies look as objects in the universe. The other shows you what it feels like to live inside one. There is also a practical side to this comparison for astronomers. Different constellations offer different kinds of research opportunities. Regions like Orion, with nearby star-forming clouds, are ideal for studying how stars and planets form. Regions far from the galactic plane are good for studying the structure of the galactic halo and for finding distant galaxies. Sagittarius, with its view into the central bulge and inner spiral arms, is crucial for understanding the dynamics, mass distribution, and evolution of the Milky Way as a whole, so each constellation becomes a kind of research window, opening onto a different aspect of the galaxy or the universe beyond it. Another subtle difference comes from how the sky feels when you move from one constellation to another. If you trace the Milky Way across the sky, you will notice that it changes in brightness and texture. In some regions it is faint and narrow. In others, like Sagittarius, it becomes wide and bright. This variation reflects the structure of the galaxy. The Milky Way is not a uniform ring of stars. It has thicker and thinner regions, arms and gaps, bulges and stretches. Sagittarius lies in one of the thickest, most luminous parts of that band. Comparing it to a constellation where the Milky Way is faint or absent can make that contrast very clear. There is also the experience of scale to consider. In a constellation like the Pleiades, you can focus on a single, well-defined cluster and get a sense of its physical size and distance. In Sagittarius, there is no single focal point that represents the whole region. Your attention is spread across many layers and features. This can make Sagittarius feel less like a destination and more like a journey. Your eye moves from one star to another, from one patch of glow to another, without ever settling on a single defining object. Another way to compare constellations is by how they frame the Milky Way story. Some point toward regions of ongoing starbirth. Others point toward older, quieter parts of the galaxy. Sagittarius points toward a mix of both, with ancient stars in the central bulge and active star-forming regions in the inner arms. So in a sense, Sagittarius offers a cross-section of the galaxy's life cycle, from old to young, from dense to diffuse. This richness can make it feel more complex than many other constellations, even if its outline is less immediately striking. There is also the question of how big feels when you stand under the sky. A constellation that sits high overhead can feel more immersive than one that hugs the horizon, simply because more of it is within your field of view. Sagittarius, depending on your latitude, might never rise very high, or it might pass near the zenith. This can change how it compares to other constellations in a very personal, experiential way. From one place, it might feel modest and distant. From another, it might feel dominant and central. This reminds us that comparison is always relative, shaped by where you stand and how you look. When you put all of these factors together, a picture begins to emerge. Sagittarius is not necessarily bigger than other constellations in a simple physical sense. Its official boundaries cover a certain area of sky, comparable to many others. What sets it apart is the depth and richness of what lies behind it. It is a direction that opens into the heart of the Milky Way, a line of sight that spans a significant fraction of the galaxy's structure. Other constellations open into different kinds of space, quieter, thinner, or oriented outward toward the wider universe. Each one offers a different perspective on where we are and what surrounds us. Seeing Sagittarius in this comparative light can deepen your sense of what the night sky represents. It becomes less like a collection of isolated pictures and more like a map of directions, each pointing toward a different aspect of a vast interconnected system. Stepping back from the individual stars and patterns of the sky, there comes a moment when the word big itself starts to feel a little uncertain, as if it were a tool designed for a world much smaller than the one it is being asked to describe. In everyday life, big usually means something you can compare directly. A house is bigger than a car, a hill is bigger than a building, a country is bigger than a city. These comparisons work because all of these things exist within a shared scale. one where distances and sizes can be held in the mind without breaking apart. But when you turn that same word toward the cosmos, especially toward something like Sagittarius, it begins to stretch in ways that challenge its original purpose. To begin unpacking this, it helps to notice how many different meanings big can take on, even before you leave Earth. Something can be big in terms of physical size, big in terms of mass, big in terms of influence, or big in terms of importance. A small object can have a big impact. A large object can be relatively insignificant in its surroundings. The word shifts depending on what you're focusing on. In the context of the universe, those different meanings of big become even more distinct. There is physical size measured in kilometers, light years, or even larger units. There is mass, measured in terms of how much matter something contains and how strongly it pulls on everything around it. There is spatial extent, how much volume something occupies. There is temporal extent, how long something lasts or how far back in time it reaches through the light it sends us. Sagittarius, as a constellation, touches on all of these at once, which is part of why the question of how big it is never settles into a single simple answer. If you think of big as physical size in the most literal sense, then Sagittarius, as a pattern, does not have a size at all. There is no object out there that you can measure from one edge to another and say, "This is Sagittarius." The stars that form its outline are scattered across a wide range of distances, and the space between them is mostly empty. In that sense, Sagittarius is not big or small, it is a perspective. But if you shift your focus to the region of space it points toward, the word big suddenly becomes more meaningful. The line of sight through Sagittarius stretches from our local spiral arm, across inner arms, into the central bulge of the Milky Way, and potentially beyond. That is a physical distance measured in tens of thousands of light years. In that sense, Sagittarius is big because it represents a deep slice of an entire galaxy. Now consider mass. The stars you see in Sagittarius include some that are much more massive than our Sun. Giant and supergiant stars that contain many times its mass and shine with far greater energy. Beyond them, near the galactic centre, lies a supermassive black hole with a mass of about 4 million suns. The total mass of the region of the galaxy you're looking toward is enormous. It includes billions of stars, vast clouds of gas, and a large amount of dark matter that does not emit light at all but still contributes to the galaxy's gravitational structure. So in terms of mass, the direction marked by Sagittarius points toward one of the most massive and influential regions of the Milky Way. Then there is influence, which is another way of thinking about big. Something can be physically small but exert a large influence. Sagittarius, a star, the black hole at the centre of the galaxy, is a good example. It is smaller in size than our solar system, yet its gravity helps shape the motion of stars in the inner galaxy. In that sense, big does not mean wide or tall or long. It means powerful. Sagittarius, as a marker of that region, becomes associated with that power, even though the black hole itself is invisible in ordinary light. Another dimension is time. When you look at Sagittarius, you're seeing a mixture of moments from different eras. The nearest stars are being seen as they were a few hundred years ago. The stars near the galactic centre are being seen as they were tens of thousands of years ago. So the region is big in time as well as in space. It spans a wide range of history, all layered into a single view. This temporal scale can be just as difficult to grasp as the spatial one. Human history, even when you stretch it back to the earliest civilizations, covers only a few thousand years. The light from the farthest stars in Sagittarius began its journey long before that. It was travelling through space while ice sheets covered large parts of the Earth, while humans were still learning to shape stone tools, while the landscapes we know today were still taking form. So when you look in that direction, you are not just looking far away, you are looking far back. Another way to think about big is in terms of complexity. A simple object might be physically large but structurally straightforward. A more complex system might be physically smaller, but rich in interactions and layers. Sagittarius, as a region of the sky, is complex. It includes nearby stars, distant stars, star clusters, nebulae, clouds of gas and dust, and the dynamic environment of the galactic center. These components interact through gravity, radiation, and motion, creating a constantly evolving structure. In that sense, Sagittarius is big in terms of the number of processes and phenomena it contains. There is also the idea of big, as in big picture. Something can be big not because it is physically large, but because it helps you understand something larger. Sagittarius plays this role in astronomy. By studying the region it points toward, scientists learn about the structure of the Milky Way, the behavior of stars near a supermassive black hole, the distribution of mass in the galaxy, and the processes that drive star formation in dense environments. So Sagittarius is big in the sense that it opens onto some of the most important questions about our galaxy and our place within it. All of these meanings can exist at once, and that is where the word begins to feel stretched thin. It tries to cover physical size, mass, influence, time, complexity, and significance, all with the same simple label. This can lead to a kind of quiet confusion. When someone asks how big Sagittarius is, what are they really asking? Are they asking how wide it looks in the sky? How far away its stars are? How much of the galaxy it points toward? How massive the region is? How important it is to our understanding of the cosmos? Each of those questions has a different answer, and none of them cancels out the others. Another layer to this is the role of scale. In everyday life, we move between a limited range of sizes. We deal with meters, kilometers, maybe the size of a city or a country. Our intuition is shaped by those experiences. In astronomy, the scales jump by enormous factors. A planet is small compared to a star is small compared to a galaxy is small compared to a cluster of galaxies. A cluster is small compared to the large-scale structure of the universe, so something that feels big at one level can feel small at another. Sagittarius is a good example of this shifting scale. As a constellation, it is one of many patterns in the sky. It covers a certain area, comparable to others. In that context, it is not uniquely large. As a line of sight into the Milky Way, it represents a significant fraction of a galaxy. In that context, it feels very large. As part of the universe as a whole, even the Milky Way is just one of hundreds of billions of galaxies. In that context, Sagittarius becomes a very small piece of a much larger picture. This layered scaling can be disorienting, but it can also be gently grounding. It reminds you that big is always relative. There is always a larger context. There is also a personal scale to consider. From a human perspective, even the nearest star is unimaginably far away. The distances involved in Sagittarius, whether hundreds or tens of thousands of light years, are far beyond anything we can experience directly. So on a personal level, everything in the night sky is big in the sense that it is beyond reach, beyond touch, beyond direct interaction. But within the context of astronomy, those same distances are measured, compared, and mapped. They become numbers in tables, points in models, steps in a larger understanding. So big can mean different things to different observers. To a stargazer lying under the night sky, Sagittarius might feel big because it draws the eye and fills the view with light and shadow. To an astronomer, it might feel big because it encompasses a large and complex region of the galaxy. To a cosmologist, it might feel small because it is just one direction among many in a vast universe. Another subtle meaning of big comes from the idea of connection. Something can feel big because it connects many things together. Sagittarius connects our local neighborhood of stars to the distant galactic center. It connects visible light to invisible radio waves and infrared radiation. It connects ancient human stories about archers and teapots to modern scientific ideas about black holes and galactic structure. In that sense, it is big in terms of the range of ideas and perspectives it brings together. There is also the way big can be tied to the feeling of awe. Something might not be the largest thing in existence, but it can still inspire a sense of vastness or wonder. Sagittarius often does this because of its richness. The glowing band of the Milky Way, the dense star fields, the idea that you are looking toward the heart of a galaxy, all combine to create an experience that feels expansive. That feeling is not a direct measurement of physical size. It is a response to the idea of scale, depth, and connection. Another aspect to consider is how big changes with knowledge. When you first learn the names of constellations, they might feel like simple shapes, small pieces of a large sky. As you learn more about what lies behind them, their significance can grow. Sagittarius might start as a teapot shape you use to find your way around the sky. Then it becomes the direction of the galactic center. Then it becomes a region associated with a supermassive black hole and dense star clusters. Then it becomes part of the story of how galaxies form and evolve. So big can also mean big in meaning, not just big in size. This layering of meaning can make the sky feel like a kind of book, where each region has multiple levels of interpretation. You can read it at a surface level, enjoying the patterns and the beauty. Or you can read it more deeply, connecting those patterns to the structure and history of the universe. Sagittarius offers a particularly rich chapter in that book, because it touches on so many fundamental aspects of astronomy at once. There is also a mathematical side to big that often stays in the background of these reflections. Astronomers use numbers like light years, parsecs, and solar masses to quantify what they observe. These units are tools designed to handle the immense scales of the cosmos. A parsec, for example, is about 3.26 light years. It is based on the geometry of parallax, the tiny shift of a star's position as Earth orbits the Sun. It is a way of turning a small angle into a large distance. When astronomers say the galactic center is about 8 kiloparsecs away, they are using this system to express a distance that is otherwise difficult to write down or visualize. These numbers make big manageable in a technical sense, but they do not necessarily make it intuitive. You can understand that 26,000 light years is a large distance, but it is hard to feel it. This gap between understanding and feeling is part of the experience of cosmic scale. You can know the numbers without fully internalizing what they mean. Sometimes metaphors help bridge that gap. You might imagine shrinking the galaxy down so that the distance from the Sun to the center is like the distance from your home to a distant city. Or you might imagine the light from the galactic center as a message that has been traveling since the last ice age. These comparisons do not make the scale exact, but they give it a shape in the mind. Another layer to big is how it relates to change. Large systems often change slowly. The galaxy evolves over billions of years. The position of stars shifts over millions. The structure of spiral arms reshapes over long time scales. From a human perspective, these changes are almost imperceptible. The sky looks the same night after night, year after year. Sagittarius rises and sets, season after season, in a familiar rhythm. So big can also mean slow, in the sense that large-scale changes take a long time to unfold. This can be oddly comforting. It suggests a kind of stability, even in a universe that is constantly in motion. At the same time, within that slow, large-scale structure, there are small, fast events. Stars flare, supernovae explode, gas clouds collapse. These local changes can be dramatic, even though they take place within a much larger, slower-moving system. So Sagittarius, as a region, contains both the slow and the fast, the ancient and the immediate, the vast and the small. When you put all of these meanings together, the word big begins to feel like a doorway rather than a label. It opens into questions about scale, perspective, influence, time, and connection. Asking how big Sagittarius is becomes a way of asking how we fit into the universe. It becomes a way of exploring the relationship between a small conscious observer on a planet and a vast, complex galaxy that has been evolving for billions of years. That relationship is not one of simple comparison. It's not about measuring ourselves against something larger. It is about recognizing that we are part of a system that spans scales far beyond our immediate experience. Sagittarius, pointing toward the heart of the Milky Way, makes that recognition particularly tangible. It gives you a direction in the sky that corresponds to a direction in the structure of the galaxy. So when you look there, you're not just looking at stars. You're looking along a line that connects your local, everyday world to a much larger, deeper and older system. That connection can quietly shift what big means. It becomes less about size alone and more about relationship, how things relate to one another across space and time. Long before anyone ever thought to call this pattern an archer, before bows and arrows were carved into stories and mapped onto the stars, the points of light we now connect as Sagittarius were already on their own quiet journeys through the galaxy. They did not arrive in this arrangement together. They did not form as a group. They simply happened, for a brief moment in cosmic time, to line up in a way that a human eye could recognize and remember. That idea alone begins to soften the sense of permanence we often attach to the night sky. The shapes feel ancient, unchanging, almost eternal. Yet the universe they belong to is anything but still. Every star you see in Sagittarius is moving. Some drift slowly, some more quickly, each following its own path around the centre of the Milky Way. These motions are not random. They're guided by gravity, by the combined pull of billions of other stars, clouds of gas, dark matter, and the massive black hole at the heart of the galaxy. Together they create a slow, sweeping circulation that carries everything along. From our point of view on Earth, these motions are usually too subtle to notice. A star does not visibly slide across the sky from one night to the next. Even over a lifetime, the changes are almost imperceptible without careful measurement. The sky feels fixed, reliable, the same pattern repeating itself season after season. But if you stretch your sense of time beyond years and generations, beyond written history and even beyond the age of our species, a very different picture begins to emerge. Astronomers use the term proper motion to describe how stars move across the sky relative to more distant background stars. This motion is measured in tiny angles per year, often just a fraction of an arcsecond. That is a shift so small that it takes specialized instruments and long periods of observation to detect. Yet those tiny shifts add up. Over thousands of years, stars noticeably change their positions. Over tens of thousands, the familiar outlines of constellations begin to bend and stretch. Over hundreds of thousands and millions, the patterns dissolve entirely and reform into new, accidental arrangements. Sagittarius is no exception. Some of the stars that make up its brighter foreground are relatively close to us in galactic terms. Because of that, their proper motions are larger than those of more distant stars. They drift more quickly across our field of view. Meanwhile, the distant stars near the galactic centre move more slowly in apparent terms, even though their actual speeds through space can be just as high. Their great distance makes their motion look smaller from our perspective. This difference in apparent motion means that the shape of Sagittarius will not change evenly. Some parts of the pattern will stretch and shift faster than others. Over long timescales, the alignment that defines the teapot, or the archer, will gradually break apart. If you could watch the sky in a kind of accelerated time-lapse, spanning tens of thousands of years in a few seconds, you would see the stars of Sagittarius slide across the background like slow-moving fireflies. Lines would bend, angles would open and close, familiar groupings would drift apart. Eventually the shape would become unrecognizable. The archer would lose its bow. The teapot would spill its last imaginary drop. New shapes might form by chance, patterns that future observers could name and tell stories about. This transformation is not unique to Sagittarius. All constellations are temporary, in this deep time sense. The sky's a living map, constantly being redrawn by the motion of its stars. But Sagittarius has an additional layer of time woven into it, because of the depth of the region it points toward. When you look at the distant stars near the galactic centre, you're seeing them as they were tens of thousands of years ago. The light you receive tonight left those stars long before any modern civilization existed. During that time, those stars have continued to move along their orbits. They are not where you see them now. They have shifted, perhaps by small amounts, perhaps by more, depending on their speeds and paths. So the picture of Sagittarius you see is not just a snapshot of space. It is a collage of different moments in time. The nearer stars are shown as they were a few hundred years ago. The farther ones are shown as they were thousands or tens of thousands of years ago. This means that the shape of the archer is, in a sense, already out of date. It is not a picture of how the stars are arranged now in some universal present. It is a picture of how they were arranged across a span of history, compressed into a single view by the finite speed of light. That layering of time adds another subtle way in which the shape is always changing, even if we cannot see the change directly. There is also the motion of our own planet to consider. Earth's axis slowly wobbles, a movement called precession. This wobble changes the orientation of Earth in space over a cycle of about 26,000 years. Because of this, the position of the constellations relative to the seasons gradually shifts. Thousands of years ago, Sagittarius rose at different times of year than it does today. Thousands of years from now, it will do so again. So the archer does not just change shape internally as its stars move. Its relationship to our calendar and our seasons changes as well. In ancient times, Sagittarius might have been associated with different seasonal events, different cultural markers, different stories tied to planting, harvesting, or migration. Those connections drift over time, just as the stars drift across the sky. This slow shift can be seen in the history of astrology and ancient astronomy. The zodiac signs no longer align with the constellations they were originally named after because of precession. The sign of Sagittarius, for example, is no longer in front of the constellation Sagittarius during the same part of the year it was in ancient times. This is another way time quietly reshapes the archer, not in its physical form but in its cultural meaning. Beyond these gradual motions, there are also more dramatic, though rarer, changes that can affect the region. Stars are born and stars die. In the dense inner parts of the Milky Way, star formation is more active than in our local neighbourhood. Clouds of gas collapse under gravity, ignite new stars, and light up their surroundings with radiation and stellar winds. Over millions of years, these processes can add new bright stars to the region, or remove them when they explode as supernovae or fade into dim remnants. A particularly bright supernova in Sagittarius would be a spectacular event, visible from Earth even in daylight. It would temporarily add a new, brilliant point of light to the pattern, changing its appearance for weeks or months. There is historical evidence that such events have occurred in other parts of the sky, recorded by ancient observers who noted new stars appearing where none had been before. In Sagittarius, such an event would leave a lasting mark on the structure of the region, even after the visible flash faded. The expanding shell of gas from the explosion would interact with the surrounding clouds, possibly triggering the formation of new stars. So time changes the archer not only through the slow drift of stars, but also through these occasional powerful moments of creation and destruction. On even longer timescales, the galaxy itself changes. The Milky Way is not a finished static structure. It continues to evolve by interacting with its surroundings. It absorbs smaller galaxies that wander too close. It is influenced by the gravitational pull of its neighbours in the local group, especially the Andromeda Galaxy. Over billions of years, these interactions reshape the galaxy's structure. Spiral arms can shift and fade. The central bulge can grow. The overall distribution of stars can change. In the distant future, the Milky Way and Andromeda are expected to collide and merge, forming a new, larger galaxy. When that happens, the region we now call Sagittarius will be part of a completely different structure. The galactic centre will be a combined core with a much larger mass and a different shape. The line of sight from Earth, if Earth still exists in any form, will point toward a very different cosmic environment. So in the longest sense, time will not just change the shape of the archer. It will change the entire context in which the archer exists. There is also the subtle role of dark matter in this long-term evolution. The Milky Way is embedded in a vast halo of invisible mass that extends far beyond the visible disk. This dark matter influences how stars and gas move, how the galaxy holds together, and how it interacts with other galaxies. As the galaxy evolves, this unseen framework shapes the paths of stars, including those in Sagittarius. It is another quiet force guiding the slow transformation of the pattern. All of these processes operate on timescales that are difficult to hold in the mind. Thousands of years, millions, billions. From a human perspective, the sky feels almost eternal. The same stars that guided ancient travellers still guide us. The same constellations that were named in long-vanished cultures still appear in our books and apps. But from a cosmic perspective, those patterns are fleeting. Sagittarius, as a recognisable shape, is a temporary arrangement in a much longer story. It is a moment of alignment, a coincidence of perspective that happens to last long enough for a species like ours to notice and name. There is something quietly humbling in that realisation. The Archer is not a fixed landmark in an unchanging universe. It is part of a flow, a moving, evolving system in which even the most familiar things are in motion. This does not make the pattern less meaningful. In some ways, it makes it more so. The fact that we happen to live at a time when this particular arrangement exists gives it a kind of fleeting significance. We are witnesses to a specific version of the sky, one that has not always existed and will not always exist. Another layer of time's influence comes from our own changing relationship to the stars. As technology advances, our ability to observe and understand Sagittarius changes. A few centuries ago, people saw only the brightest stars and the faint glow of the Milky Way. With the invention of telescopes, they began to see clusters and nebulae. With photography, they captured details invisible to the eye. With radio and infrared telescopes, they revealed the hidden structure of the galactic centre. So even if the physical shape of the Archer changes slowly, our picture of it changes more quickly as our tools and knowledge evolve. In that sense, time reshapes Sagittarius in our minds as well as in space. The region has gone from being a mythological figure to a navigational aid, to a window into the structure of the galaxy and the behaviour of black holes. Each stage adds a new layer of meaning. This evolution of understanding is part of the story of science itself, a gradual deepening of perspective rather than a sudden leap. There is also the role of memory to consider. The names and stories attached to Sagittarius are carried forward through generations, even as the stars themselves slowly drift. So the Archer exists not just in the sky, but in human culture. It is a shared reference point, a piece of a long collective conversation about the night. As time passes, those cultural meanings can change, fade, or be replaced, just as the physical pattern will eventually change. Future civilizations, if they exist, might look at the same region of sky and see something entirely different, both in shape and in story. They might not recognize an archer or a teapot. They might draw different lines, tell different tales, or focus on different aspects of the region, such as the glowing core of a merged galaxy or the aftermath of cosmic collisions. This thought can gently widen the sense of time beyond even the movement of stars. It includes the movement of ideas, stories, and ways of seeing. So when you consider how time changes the shape of the Archer, you're really considering several layers at once. There is the physical motion of stars through the galaxy, slowly altering their positions relative to one another. There is the finite speed of light, which means you are always seeing a mixture of different moments in the past. There is the wobble of Earth's axis, which shifts the archer's place in the rhythm of the seasons. There are the births and deaths of stars, adding and removing points of light from the region. There is the long-term evolution of the galaxy itself, reshaping the broader structure Sagittarius points toward. And there is the changing human perspective, reshaping what the pattern means and how it is understood. All of these forms of time overlap in a single view of the night sky. The result is something that feels both stable and fluid at the same time, stable enough to be recognized across generations, fluid enough to be part of a universe that never truly stands still. If you let that idea settle, the sky can begin to feel less like a fixed ceiling and more like a slow-moving river, carrying stars, light, and meaning along with it. Sagittarius becomes a moment in that flow, a pattern that exists for a while, long enough for us to notice, to name, to study, and to wonder about. And as that sense of motion and change becomes part of the background, it naturally leads into another gentle question. If the shape of the archer is not permanent, if it is drifting and evolving along with everything else in the galaxy, what might it look like far into the future when the stars have moved, the galaxy has changed, and the night sky above our planet, or whatever remains of it, tells a very different story than the one we see tonight? Far into the future, long after the familiar outlines of today's night sky have faded from memory, the region we now call Sagittarius will still exist as a direction in space, but the scene it presents will be shaped by motions and changes that are already quietly underway. Nothing dramatic needs to happen all at once for the view to become different. The steady, patient movement of stars, the slow turning of the galaxy, and the gradual evolution of stellar populations will be enough to transform what an observer might see when they look toward that part of the sky. To begin imagining this future, it helps to anchor yourself in the kind of timescales involved. 1,000,000 years sounds immense by human standards, but in the life of a galaxy, it is a relatively short interval. The Milky Way is more than 10 billion years old. Its spiral arms, its central bulge, and its population of stars have been forming and reforming for a span of time that dwarfs the entire history of our species. So when we talk about what Sagittarius will look like millions of years from now, we are really talking about a gentle shift, not a complete reinvention. The galaxy will still be here. The general structure of the Milky Way will still be recognizable. The central bulge will still dominate the inner regions, but the details, the exact placement of stars and the specific patterns they form in our sky, will be different. The most immediate and consistent change will come from the motion of stars through the galaxy. Every star in Sagittarius is orbiting the center of the Milky Way. The Sun does the same. These orbits are not perfect circles, and they are not synchronized. Some stars move faster, some slower. Some follow paths that take them closer to the galactic plane, while others wander above and below it. Over 1,000,000 years, a typical star in our region of the galaxy might travel dozens of light years along its orbit. That might not sound like much compared to the scale of the Milky Way, but it is enough to noticeably change the apparent arrangement of stars in the sky. The nearer stars, in particular, will show the most dramatic shifts. Their proper motion will carry them across the background of more distant stars, altering the familiar lines and angles that define the pattern of Sagittarius. Imagine taking a photograph of the night sky today, and then another one 1,000,000 years from now from the same location in space. When you overlay the two, the differences would be clear. The brightest foreground stars would have moved to new positions. Some that are close today might have drifted far enough away in angle that they no longer sit within the same recognizable shape. The more distant stars, especially those near the galactic center, would appear to move more slowly in apparent terms. They would still shift, but their great distance would make their motion subtler. The result would be a pattern that feels stretched and rearranged. Some of the familiar groupings might still be there, but the overall outline of the archer would be distorted. Another change would come from the life cycles of stars themselves. Stars are not permanent fixtures. They are born, they live for millions or billions of years, and they eventually die. The length of a star's life depends largely on its mass. Small, cool stars can burn quietly for tens or even hundreds of billions of years. Massive, bright stars live fast and die young, sometimes just a few million years. Sagittarius includes a mix of both types, but many of its most prominent bright stars are relatively massive. That means their futures are already set on a shorter timeline. Over the next few million years, some of these stars may reach the end of their lives. They might swell into red giants, shedding their outer layers into space. Or, if they are massive enough, they might explode as supernovae, briefly becoming some of the brightest objects in the galaxy, before fading into neutron stars or black holes. If a supernova were to occur in the region of Sagittarius, it would be a spectacular event for any observers alive at the time. A new point of light could appear in the sky, bright enough to be seen during the day, changing the appearance of the constellation for weeks or months. After the explosion faded, the region would be left with a glowing remnant, an expanding shell of gas and dust that could persist for thousands of years, interacting with surrounding material and possibly triggering the formation of new stars. So the future of Sagittarius is not just a story of stars moving. It is also a story of stars appearing and disappearing, of light being added and taken away. Another layer of change comes from the motion of our own solar system. The Sun is orbiting the galactic center, taking about 225 to 250 million years to complete a full circle. Over a million years, it will move a noticeable distance along that path, though still a small fraction of the total orbit. This movement changes our perspective on the galaxy. The direction we look to see the center will shift slightly. The relative positions of stars in the sky will be affected by this change in viewpoint. So even if the stars themselves were frozen in place, the sky would still look different because we would be looking from a new position. This combination of stellar motion and observer motion means that the future sky is shaped by a kind of double drift. Everything is moving, including the point from which the movement is observed. The result is a constantly evolving picture, even if the changes are slow and subtle on human timescales. There is also the influence of the spiral arms to consider. The Milky Way's spiral arms are not solid, fixed structures. They are patterns of higher density that move through the disk of the galaxy. Stars and gas flow into these regions, form new stars, and then drift out again. Over millions of years, the position of the spiral arms relative to the Sun will change. Our solar system may move closer to or farther from an arm. The line of sight towards Sagittarius will pass through different regions of the galaxy's structure. This can affect how rich and crowded the background of stars appears. If our line of sight passes through a denser region of a spiral arm, the sky in that direction might become more filled with star clusters and nebulae. If it passes through a more sparse region, the background might thin out. So the future appearance of Sagittarius could be influenced by where our solar system is relative to these large-scale patterns in the galaxy. Another factor is the gradual evolution of the galactic center itself. Sagittarius A star, the supermassive black hole at the heart of the Milky Way, is not static. It slowly accretes matter from its surroundings. Gas and dust spiral inward, heating up and emitting radiation before disappearing beyond the event horizon. Over millions of years, the black hole's mass will grow, though very slowly compared to its current size. The environment around it may change as star formation continues in the dense inner regions, and as stars pass close enough to be disrupted by its gravity. These processes can alter the distribution of light and matter near the center, which in turn can affect the glow and structure of the central bulge as seen from afar. So the deep background of Sagittarius, the part that represents the heart of the galaxy, is also evolving. There is also the role of interstellar dust and gas. The dark lanes and glowing clouds you see in Sagittarius are part of a constantly changing interstellar medium. Clouds collapse to form stars. stellar winds and supernovae blow material back into space. Radiation from hot stars erodes and reshapes nearby clouds. Over millions of years, the arrangement of these clouds will change. Some dark patches may disperse, revealing stars that were once hidden. New clouds may form in other places, creating new areas of obscuration. This means that the texture of the Milky Way and Sagittarius, the pattern of light and dark, will slowly shift. In some future view, regions that are dark today might glow with starlight, and regions that are bright today might be crossed by new shadows. Another aspect to consider is the long-term evolution of the galaxy as a whole. The Milky Way is not isolated. It is part of a group of galaxies that are gravitationally bound to one another. Over billions of years, these galaxies interact, pass by, and sometimes merge. The most significant future event for the Milky Way is its eventual collision with the Andromeda Galaxy. This is expected to happen in about 4 to 5 billion years. That timescale is much longer than millions of years, but it is part of the broader future that shapes the ultimate fate of Sagittarius. During and after this merger, the structure of the galaxy will change dramatically. The spiral arms will be disrupted, the central bulges will combine, the orbits of stars will be altered on a grand scale. In that distant future, the region we now call Sagittarius will be part of a very different kind of galaxy, possibly an elliptical or irregular one, rather than a spiral. The concept of a galactic center as we understand it today may change, as the two central black holes merge and the combined system settles into a new equilibrium. From the perspective of an observer in that far future, the sky would be almost unrecognizable compared to what we see now. But even before such dramatic events, the slow, steady changes of millions of years will already have reshaped the familiar pattern. Another subtle change comes from the evolution of the Sun itself. In about 5 billion years, the Sun will begin to leave the main sequence and expand into a red giant. Long before that, over the next few 100 million years, its brightness will gradually increase. This change in brightness will affect the conditions on Earth, but it will also affect how the night sky appears, at least indirectly. If the Sun becomes brighter, the contrast between the night sky and the daytime sky might change for any observers still on or near Earth. This is a more speculative layer, but it highlights the fact that the future appearance of Sagittarius is tied not just to the stars in that region, but also to the state of the observer and their environment. Another dimension to consider is how technology might shape future views of the sky. Even today, our understanding of Sagittarius is very different from what it was a few centuries ago. We can observe in wavelengths beyond visible light. We can track the motion of stars near the galactic center. We can map the distribution of gas and dust across the galaxy. In millions of years, if intelligent observers still exist, their tools and knowledge may be far more advanced. They may be able to see structures and processes that are completely hidden to us now. So the look of Sagittarius in the future may be shaped as much by the way it is observed as by the way it physically changes. From a more grounded perspective, imagine a future stargazer standing under a dark sky, looking toward the region that we now call Sagittarius. They might see a pattern of stars that only faintly resembles the Archer or the Teapot. Some of the bright points we rely on today might be gone, replaced by new ones. The Milky Way's band might be textured differently, with new glows and shadows. They might have different names for the patterns they see, different stories, different ways of navigating the sky. But behind all of that, the same fundamental structure would still be there, at least for a long while. A galaxy with a dense center, stars orbiting in a vast disk, clouds of gas forming new suns. The line of sight would still lead inward, toward the heart of a system that is billions of years old and still evolving. There is a quiet continuity in that idea. Even as the details change, the larger context remains. Another interesting way to think about the future of Sagittarius is to imagine how it would look from a different place in the galaxy. As the Sun continues its orbit, our position relative to the central bulge will change. The angle at which we view the inner galaxy will shift. The thickness and brightness of the Milky Way in that direction may appear different. So the future appearance of Sagittarius is not just about the stars moving within it. It is also about the observer moving around it. This can make the idea of a fixed constellation feel even more temporary. It is not just the pattern that changes, the point of view changes too. There is also the role of gravitational interactions on smaller scales. Stars can pass close to one another, altering their orbits slightly. In dense regions, such interactions are more common. Over millions of years, these small changes can accumulate, subtly reshaping the distribution of stars in certain parts of the galaxy. In the inner regions near the galactic center, where Sagittarius points, such interactions are particularly frequent. This adds another layer of motion and change to the future of the region. Another thought to hold alongside all of this is the persistence of light itself. The light from stars in Sagittarius that will reach Earth millions of years from now has not yet been emitted. It will be produced by stars that may not even exist yet, stars that will form in clouds that are currently dark and cold. So the future appearance of Sagittarius includes stars that are not yet born. This is a powerful way to think about time in the sky. The view you see tonight is a mix of past and present. The view in the future will be a mix of present and future from our perspective. This continuous flow of light, always arriving from different moments, is what makes the sky a living record of cosmic history. As you imagine the Archer millions of years from now, you can picture a region that is both familiar and new. The deep glow of the Milky Way still marks the inner galaxy. The sense of depth and richness is still there, but the specific points of light, the exact shapes and alignments, have shifted. It is like looking at a river that has changed its course over time. The water is still flowing, the banks are still there. But the details of the landscape are different. There is also a philosophical side to this future view. The idea that the sky will change, that the patterns we recognize are temporary, can shift how you think about your own place in time. We often think of the stars as symbols of permanence, of something that outlasts everything else. In a sense, they do. Individual stars can live for billions of years, far longer than any human civilization. But even they are part of a process, a cycle of birth, life, and death, set within a larger, evolving structure. Sagittarius, as a pattern, is a fleeting moment in that process. Recognizing this does not diminish its beauty or significance. It adds a layer of depth to it. The pattern becomes not just something to admire, but something to witness, a temporary alignment in a vast, ongoing story. As that idea settles in, the future of Sagittarius becomes less about predicting a specific shape, and more about appreciating the nature of change itself. The region will continue to be a gateway to the inner galaxy, even as the details shift. It will continue to point toward a center of mass and influence, even as that center grows and evolves. And for any observers who look up at the sky in that distant future, it will continue to offer a sense of depth, connection, and curiosity, even if the names and stories attached to it are entirely different from our own. As your attention drifts back from those distant futures and long unfolding timelines, there is a gentle shift that can happen, almost without noticing, when you return to the present moment and the simple act of looking up. The sky above you, right now, is not a diagram or a projection or a map of light years and galactic structures. It is a quiet field of points and glows, a scene that meets your eyes in the same way it met the eyes of countless people before you, each of them standing in their own place and time, carrying their own questions and stories into the night. Sagittarius in this moment is not a corridor through the Milky Way or a marker for a supermassive black hole. It is a shape, or maybe just a suggestion of one. It is a cluster of brighter and dimmer lights that you can trace if you choose, or simply let blur into the wider glow of the galaxy if you do not. This is where perspective begins to soften. After thinking about distances measured in tens of thousands of light years, about motions that unfold over millions of years, and about changes that reshape entire galaxies, it can be strangely calming to notice something much smaller. The way a single star flickers slightly as Earth's atmosphere bends its light. The way a patch of the Milky Way seems to brighten when your eyes adjust to the dark. The way a breeze or a sound from the ground below reminds you that you're standing or sitting or lying down on a very solid, very immediate world. In that contrast between the vast and the close, something quietly settles into place. The question of how big Sagittarius really is no longer feels like something that needs a precise answer. It becomes more like a doorway into a way of seeing. Big can mean deep, it can mean wide, it can mean old, it can mean powerful, it can mean meaningful, and it can also mean simply enough to make you pause. One of the subtle gifts of looking at the sky this way is that it can loosen the edges of everyday concerns. Problems that feel large in the context of a single day or a single life can feel different when placed alongside a structure that spans a galaxy. That does not make those problems disappear, but it can change how tightly they hold your attention. Sagittarius, pointing toward the heart of the Milky Way, can become a kind of reminder that you are part of something much larger, even if you never travel farther than the space around your own home. There's also a kind of quieter quality in this view. Every person who looks up at this region of the sky, no matter where they are or who they are, is looking at the same general direction in the universe, the same central bulge of the galaxy, the same dense fields of stars, the same deep structure that holds everything in its slow, steady orbit. Your perspective is unique, shaped by your location on Earth, your moment in history, your own experiences and thoughts. But the larger backdrop is shared. That shared backdrop can create a sense of connection that does not rely on words or explanations. It is simply there, available to anyone who takes the time to notice it. Another layer of wonder comes from the idea that the light you are seeing has travelled so far to reach you. Each point of light in Sagittarius has its own story of movement through space, of passing through dust and gas, of being bent and scattered slightly by the medium it travels through. By the time it reaches your eyes, it has become part of your experience, part of your awareness, even if only for a moment. That moment is brief, but it is also a kind of meeting, a quiet intersection between your life and a star that exists far beyond anything you can touch or visit. This meeting does not require you to understand the physics behind it or the distances involved. It simply happens as light enters your eyes and becomes part of what you see. There is something gentle about that simplicity. After exploring how Sagittarius stretches across the Milky Way, how it points toward hidden centers and evolving structures, how its shape changes over time, and how its future will unfold long after we are gone, it can feel grounding to remember that all of this complexity is, in practice, experienced as a calm pattern in the night sky. You do not need to hold all the layers of meaning at once. You can let them come and go, focusing on what feels most natural in the moment. Some nights, Sagittarius might just be a faint glow on the horizon, something you barely notice. Other nights it might stand out clearly, a rich textured band of light that draws your gaze and holds it. Both experiences are valid. Both are part of the same sky. There is also a kind of quiet beauty in the fact that the universe does not demand your attention. It does not announce its scale or its age or its complexity. It simply exists, and you can choose how deeply you want to engage with it. You can look up and enjoy the pattern without thinking about black holes or spiral arms. Or you can let your thoughts travel inward, across tens of thousands of light years, to the dense, energetic core of the galaxy. Or you can do a little of both. This freedom of perspective is part of what makes stargazing such a personal experience. For some people, the night sky is a place of navigation, a way to find directions and seasons. For others, it is a place of stories, of figures and myths drawn between the stars. For others still, It is a field of data, of measurements and models and theories about how the universe works. Sagittarius can be any or all of these things depending on how you approach it. The idea of wonder does not have to be dramatic or overwhelming. It can be quiet and steady, like the feeling of realizing that something familiar contains more depth than you first thought. You might find that after spending time thinking about how Sagittarius reaches into the heart of the Milky Way, the simple sight of the constellation carries a different weight. The stars themselves have not changed, but your relationship to them has. That shift in relationship is subtle. It does not necessarily come with a rush of emotion or a sudden insight. It can be as simple as a slightly longer pause, a slightly deeper breath, a moment of stillness as you look up. In that pause, the layers of scale, time, and structure you have been thinking about can soften into a general sense of presence. Another gentle aspect of this perspective is the way it can blur the boundary between the observer and the observed. When you look at Sagittarius, you're not just seeing something that exists out there. You're part of the same system. The atoms in your body were formed in stars. The sun you orbit is one of the billions of stars that make up the Milky Way. The galaxy itself is part of a larger network of galaxies moving through the universe. So in a very real sense, looking at the galaxy is a kind of self-observation. You are seeing a structure that you belong to. This idea does not have to be taken in a grand or philosophical way. It can simply sit in the background as a quiet reminder of connection. The same gravity that shapes the orbits of stars near the galactic center shapes the orbit of the sun. The same physical laws that govern the light travelling from Sagittarius to Earth govern the light reflecting off the ground beneath your feet. These are not separate realms. They are part of the same continuum. There is also something comforting in the steadiness of the larger structure. Even though stars move, patterns change, and galaxies evolve, these processes unfold slowly. The Milky Way will still be here long after individual lives, cities, and even civilizations have passed. Sagittarius, as a direction toward its center, will continue to point inward, even as the details of the view shift. That sense of continuity can be calming. It suggests that there is a larger rhythm at work, one that does not depend on the ups and downs of a single moment. At the same time, the temporary nature of the patterns we see can add a sense of preciousness to the present view. The archer, in this exact form, exists only now, in this era, from this vantage point. It did not always look this way, and it will not always look this way. The fact that you can see it like this is a small, fleeting coincidence in a very long story. This does not have to feel sad or heavy. It can feel quietly special. Another way perspective softens into wonder is through the realization that you do not need to fully understand something to appreciate it. You can know that Sagittarius points toward a supermassive black hole without needing to understand how event horizons work. You can know that the Milky Way is tens of thousands of light years across without needing to visualize what a light year really means in kilometers. The knowledge can sit alongside the experience, enriching it without overwhelming it. This balance between understanding and simply being present is part of what makes looking at the sky such a gentle activity. It can be as intellectual or as simple as you want it to be. Some people enjoy learning every detail, every name, every measurement. Others enjoy just lying back and letting the stars pass overhead. Both approaches can lead to the same quiet sense of wonder. There is also the way the night sky can create a sense of scale within the body. When you look up, your posture changes, your head tilts back, your gaze lifts, your breathing often slows just a little. These small physical shifts can mirror the mental shift of thinking about larger spaces and longer times. Sagittarius rising in the sky can become a focal point for that shift, a place where your attention rests as your thoughts drift outward. Another subtle aspect of this experience is how it can change with mood and context. On a busy night, you might glance at the sky and barely register what you see. On a quiet night, you might find yourself drawn into it, noticing details you usually overlook. The same region of stars can feel ordinary or extraordinary, depending on what you bring to it. This is another way in which big becomes relative. The sky does not change, your perspective does. There is also the way memory can become attached to certain views of the sky. You might remember a particular night, a particular place, a particular moment when Sagittarius was visible and something in your life felt different. Over time, that memory can become part of how you see the constellation, adding a personal layer to its already rich structure of distance and time. In this way, the Archer becomes not just a cosmic feature, but a marker in your own story. This blending of the personal and the cosmic is part of what gives stargazing its unique quality. It connects something very small, a single life, to something very large, a galaxy, without forcing either to diminish the other. Both can exist together, each providing a context for the other. As you rest with this idea, the notion of ending can begin to feel less like a stopping point and more like a gentle return. After travelling through thoughts of size, distance, time, motion, and future change, you come back to where you started, which is simply here, now, under the sky. The questions you asked at the beginning about how big Sagittarius really is, about what it means to look at it, do not need final answers. They can remain open, something you revisit each time you look up. The sky does not close the conversation, it keeps it going. There is a kind of softness in that openness. It removes the pressure to reach a conclusion or to hold on to a single fixed idea. Instead, you can let your understanding shift and deepen over time, just as the sky itself slowly changes. On one night, Sagittarius might feel like a familiar friend, a pattern you recognize easily. On another, it might feel like a doorway into something vast and unknown. Both of those feelings can coexist, and neither needs to cancel out the other. The region of the sky that points toward the center of the Milky Way can be both a simple shape and a complex structure, both a nearby pattern and a deep, layered view into a galaxy. Holding those ideas together, without forcing them into a single definition, is part of what makes perspective soften into wonder. And in that softened state, the act of looking up becomes less about measuring and more about noticing, less about defining and more about experiencing. Sagittarius remains there, quietly marking a direction in space while you remain here quietly aware of it. Between those 2 points, light continues to travel. Gravity continues to pull, stars continue to move, and time continues to unfold. You do not have to follow all of those processes in your mind. You can simply let them be part of the background of your awareness, like a distant, steady hum. As the night goes on, the stars will shift, the sky will turn, and Sagittarius will slowly move across your field of view, carried by the rotation of the Earth beneath you. Eventually it will sink toward the horizon or fade into the glow of dawn. But the direction it points toward, the deep, dense heart of the Milky Way, will remain, even when you cannot see it. That quiet continuity can be a gentle thing to hold on to. So if you find yourself, at some point, glancing up and recognizing that familiar patch of sky, you might remember that it is not just a pattern, not just a name, not just a question about size. It is a meeting point between your immediate everyday world and a vast evolving structure that stretches far beyond what you can see. In that meeting point, perspective softens, and wonder does not need to announce itself loudly. It can simply be there, like the faint glow of the Milky Way itself, present in the background, waiting for you to notice it whenever you feel ready to look.